Hi everyone, welcome to the post-contest discussion of the Codeforces Round 984. This is TLE Eliminators and I am Abhinav. So let's get started with the first problem. Okay, so in the first problem, we have Boris Notti composes melodies. He represents them as sequence of notes where each note is encoded as an integer from 10 to 127 inclusive. The interval between two notes A and B is equal to the mod of A minus B semitones. Boris considers a melody perfect if the interval between each two adjacent notes is either 5 semitones or 7 semitones. After composing his latest melodies, he is enthusiastically shows you the collection of works. Help Boris Notic understand whether his melodies are perfect. So basically, we just need to find that we are given an array, okay, of size n, and in that we just need to find whether if we take just any two consecutive elements, their difference would be either 5 or 7. Okay. So that's what we just need to find. So a melody is perfect if the interval between adjacent notes is either 5 or 7. So if anywhere we have that any two adjacent notes, they differ by no neither 5 nor 7, it's something different, then we would answer no. Or if all of them differ by either 5 or 7, then we would answer yes. Like you can see in the first test case, 114 and 109, okay, their difference is 5, so it's a yes. Here their difference is 7, so it's a yes. Now here you can see the difference between the first two is 7, difference between the next two is 5, so it's either 5 or 7 only, so it's a yes. Then in the fourth test case, you can see the difference between first two, this is 7, this difference is again 7. Now this difference is like 42. It's neither 5 nor 7. Okay, so if at any point we have one difference which is not 7 or 5, then we would answer no. Okay, so same way we just have to check. Okay, so what we would do, n is up till 50 only, so we'll just brute force it. We'll just check for every, if any of the two consecutive intervals is not 7 or 5, then and there we would say our answer is no. Or if all of them satisfies that condition, then we would say yes. I hope the logic is also clear, so we can just directly move to the code for this. Okay, so what we would do, I took the input in a vector I of size n. I took this input. After that, I'll assign a Boolean variable f equal to 1. Initially, I'll consider that my answer is yes. F equal to 1 means yes, all of them are satisfied. Now, one by one, I would check for all, I would go to every adjacent node. So we'll run a loop from I equal to 0 to I less than n minus 1. Okay, so we are checking the difference between I and I plus 1. So we'll run, in general, we'll run loop from I equal to 0 to less than n. But if we are at n minus 1, then I plus 1 would be n. So that would not be valid. So we'll run a loop till n minus 1 only. And we'll check the difference between ai plus 1 and ai. Okay, so the absolute difference between them, if it is neither 5 and it is not 7. Okay, so I'll check. This is not equal to 5 and this is not equal to 7. If it is neither 5 nor 7, then I would say f equal to 0 and break. Then and there I would break, and yes, it doesn't satisfies my condition. And if none of them if we don't get this condition satisfied, it means all of them satisfies the condition either 5 or 7, then our f would remain 1. So if f is 1, we would output yes, otherwise we would output no. I hope this problem is clear to everyone. If there is any doubt in this, you can ask, or we'll move to the next problem. Okay, if you look at its time complexity, this input part was order of n, and then this loop is running n times. Inside it's an order of one if else condition. So this is running n times in total, and then an if condition. So overall, I would say the time complexity is order of n, and space is also order of n, which is the input array. Okay, I hope this problem is clear to everyone. We can move to the next problem now. Okay, so now let's move to problem B. In problem B, we have that Arseni came up with another business plan to sell soda from a vending machine. For this, he purchased a machine with N cells as well as K bottles. where the ith bottle is characterized by the brand index BI and the cost CI. Okay, so this guy has a vending machine which has N shelves. Okay, and along with that, he has K bottles which he would put in the vending machine to be sold, and every bottle has two characteristics. One is its brand index, okay, and another thing is its cost. Okay, now you can place any number of bottles on each shelf, but all bottles on the same shelf must be of the same brand. Okay, so if you are placing a bottle on the same shelf, then all of them should be of the same brand. Okay, you cannot place two bottles of different brands on the same shelf, and you sorry, and you can place any number of bottles on each shelf. Okay, there is no restriction on the number of bottles on each shelf you place. Now Arseni knows that all the bottles he puts on the shelves of the machine will be sold, therefore he asks you to calculate the maximum amount he can earn, and whatever bottles he puts in the shelf, they all would be sold, so you need to find the maximum amount he can earn. Okay, so how would he put the bottles into the shelves? So just he can adjust more and more bottles which would be sold at. Finally, you need to maximize the amount that he earns. Okay, so if we look at this, if we look at the first test case, what it means. Okay, this is N and this is K. Okay, so we have N equal to 3, so we have three bottles. Okay, first bottle, it belongs to brand number 2 and its cost is 6. Second bottle, it belongs to brand number 2 and its cost is 7. Third bottle, it belongs to brand number 1, its cost is 15. Now, N is 3, it means we have 3 shelves. Okay, so whatever vending machine we have, in that you can assume we have 3 shelves. Okay, so in the first shelf, here he would place some bottles. Now, in one shelf, he can place many bottles, but all of those bottles should belong to the same brand. Okay, so he can place any number of bottles. Now, in the second shelf, he would place some bottles. In the third shelf, he may place some bottles. Now, you can see that uh, bottle number 1 and 2, they both belong to the same brand, which is brand number 2. Cost for one is 6, one of them is 7. Okay, so what he can do is in the first shelf, he can place this bottle number 1, you can say, whose cost is 6, okay, which is belonging to brand number 2. Okay, this bottle can be placed, and this bottle, both of them belong to brand number 2, so this can be placed in the same shelf. And then in the next shelf, he can place this bottle 1 and 15. Okay, this is one way. This third shelf can be left empty. In this way, how much he would earn? So all of his bottles are sold. So he would earn 6 plus 7 plus 15, which is equal to 13, 15, 28. So he would earn a total of 28 rupees in total or whatever currency. So my answer would be 28 for the first test case. You can see for the first test case, answer was 28. Okay, so likewise, we need to just decide that how we would place the bottles in order to maximize our total earning. Okay, let's see the next test case. In the next test case, what we have, N is 1 and K is 3. Okay, so we have like 3 bottles and the shelf, okay, the vending machine has only one shelf. N is 1, it means it only has one shelf. Now, we need to place these 3 bottles. Okay, so what would be best in this case? In this shelf, either we would, if we place this bottle, 1 and 15, from brand number 1 costing 15. Okay, then we cannot place these bottles in the same shelf because they are from different brand. So finally, I would just have one bottle placed and my final earning would be 15. This is one way. Or other thing is, if on that single shelf, we can place this bottle from brand number 2 costing 6, or if you are placing this bottle, then this can also be placed alongside because both of them are from the same brand. So this 27 can also be placed here. Now this bottle cannot be placed here because it's from a different brand. Now my total earning would be 6 plus 7, which would be equal to 13. Okay, so now with what would be better? This case obviously would be better because here I'm earning 15, but in this case I'm earning only 13. So the maximum profit that I can get, the maximum earning that I can get, it would be 15. So my answer for the next test case, it would be 15. You can see. Okay, so that's how you need to maximize. So how would you decide that which all you need to select? So the first observation here is that for any brand, okay, like if you have two bottles of the same brand, then they would always be placed together. There is no benefit of placing these two in separate shelves. Okay, 2 6 here and then 2 7 here. Is there any benefit of placing them in separate shelves? Because in a single shelf you can place any number of bottles. You can even have infinite number of bottles in a single shelf. So all the bottles belonging to the same brand, they would be placed in the same shelf. So basically for every brand, we can calculate if like for every shelf would belong to some brand, all the bottles of that brand would be placed here. Okay, so like in this case, we were telling that the shelf number one, this shelf belong to brand number two. This shelf belong to brand number one. This shelf like does not belong to any brand. Okay, so how many different brands we have? We would place in every shelf, we would place different brands. And in that brand, whatever bottles we have, all those, the sum of all those would be the earning from that self. Okay, so basically what we can do is for every brand we can calculate the total earning from the sum of cost from that brand. So what we can do in this, we can do that from brand number 2 we are earning 6 plus 7 equal to 13. So in 2 we can store 13. For brand number 1 it's only 15, so we would store 50. So we have two options: brand number 1 earning 15, brand number 2 earning 13. Now, in the first case, we had three cells, so we placed both of them. In the second case, we had only one self, so we were able to place only one of them. So what we would do, we would sort them in decreasing order. We would try to place the greatest one first and then the smaller ones. So we place the 15 first, and then if there is more space, then we would place 13. Otherwise, we'll stop there. Okay. So basically I think you would have got the approach. What we need to do is just take the input, and now how many different brands we can have? You can look that this BI is from the range of 1 to K. Okay. So what we would do is we would make let's say basically a vector we would make in that, like in an array we would store. Okay. In an array, what we would do is, let's say we name the array as sum, which would initially have like up till K. Basically it would have like some variable for brand number 0 1 2, or starting with 1. Okay, from 1 to K it would have like 0 0 0. Initially we'll fill it up with 0. That for brand number 1 we have 0, but uh, the sum of the cost, that is what it's storing. So for brand number 1 initially we have 0. For brand number 2 we would initialize it with 0, and we would just go to every bottle. We would add sum of B. Okay, B is the brand, that plus equal to C. Okay, so if we have, let's say for this, when we go to this bottle, we would add, for brand number 2 we would add a plus 6. For brand number 2 we would add a plus 7. For brand number 1 we would add a plus 50. That's what we would do. So when we go for brand number 2 we would add a plus 6, then we would add a plus 7, it would become 13. Then for brand number 1 we would add a plus 50. So this way our sum array would become like this. In 1 we would have 15, in 2 we would have 13. Okay, then we would sort this array. We'll just sort this array in decreasing order. Okay, sort in decreasing order, and then take the first n values from that, and then take the first n values. Okay, so either it would be the first n values, or if the number of cells are less than n, then maximum of like minimum of n, or the number of cells. So we would not take n, but we will take the minimum of n comma k values. Okay, so like if K was on, if there was only two brands and number of cells were three, so we'll only need two of the cells. In the third self is not needed there. So we'll take the minimum of n or k. The first that many values, the sum of the first that many values would be our final answer, you can say. Okay. I hope it is clear. So what we are doing, like we can look at the code directly now, is we'll initialize a sum array. So it would have values till K, all initialized with 0. Okay, so it will have indexes from 0 to K, all initialized with 0. Now we would move. Okay, so we have k bottles. So we'll run a loop till k, and we'll take the input of B and C. B is our brand, C is the cost, and we'll do sum of B plus equal to C. This way, for brand B, we add a plus C to that. So after doing this, my sum array is updated. Now for every index I, we have the number of the sum of the cost for brand I. Basically, that's what my index I denotes. Now I would sort this in decreasing order. So I'm using sum.rbegin, sum.rend. So this way I'm sorting this sum array in decreasing order. Now, after sorting it in decreasing order, I would take the first min of n or k, whatever is the minimum, first that many values that would be added to my answer. Okay. So if I have only n cells, so I'll only take the first n values. Or if k is less, then I'll take just all the values, basically, if k is only the smaller one. So in answer, I would add the first n or k values. This I'm adding to my answer. So, and then I'll print my answer. I hope this code is clear to you. It was pretty simple. Basically, you had to maintain this frequency array or whatever you say, the sum array, that only you had to update. Its time complexity, if you look, this sum array is of size k, and here we have k input. So in every input, we are doing this updation part, which is order of 1. So this is order of k here. After that, this sorting, it would have a size of k. So it would be k log k. This sorting would take k into log k time. And then we have this loop running till minimum of n or k. So this is order of min of n comma k. Okay, this is order of one operation, and then we are printing the answer. So what's my final time complexity? So my final time complexity, you can see, order of k log k, and then order of n or k. So overall, it would be like, you can say either n or k log k, whichever is greater. That only we can say. So we can say overall time complexity is n plus k log k. And for the given constraints that n and k were up till 2 into 10 to the power 5, some k log k complexity is well accepted. I hope this problem is clear to everyone. Its space complexity would be, we have a sum array of size k, so order of k. Okay, will you please explain the sum array? Basically, what we are doing here is, let's say you have this. Okay, let's take a better test case to understand. Okay, here only, let's say I am in this test case only, let's say instead of 1, we had n is equal to 2 and k is equal to 4. Let's say we have one more 3 and 17, 1 and 5. Okay, let's say we have like this. And okay, let's say we have like the 1, 2, 3, 4, 5. Okay, let's say we have this test case. What we are doing is, basically, for we have only 2 cells in my vending machine. So for every bottle, first of all, I would calculate that for every brand, how much we can keep. So if we are whatever bottles we have of brand 2, they would be kept together. So I'll initialize a sum array that would store. Okay, my k is 5, so it would have indexes. Okay, 0 is like ignored. You can ignore that index. So 1, 2, 3, 4, and 5. Okay, we have these 5 indexes. In that, I would initially store 0, and then I have to just update that for brand number 2. If we are keeping a cell for brand number 2, what earning I can earn? That would be the sum of cost for brand number 2's, whatever we have. For brand number 1, it would be the sum for brand number 1's. For brand number 3, it would be the sum for brand number 3. So every time we would go to first, and we would update sum of 2 plus equal to 6. Okay, so at index 2, we are adding 6 here. Okay, here what we would do, we would do sum of 2 plus equal to 7. So at index 2, again, we are adding 7 here. It becomes 13. Here we did sum of 1 plus equal to 15. So at index 1, we added 15. It became 15. Here sum of 3 plus equal to 17. So at index 3, we added 17. Here sum of 1 plus equal to 5. So at index 1, we added 5, it became 20. So now my final array has index 1 has 20, index 2 has 13, index 3 has 17, and the remaining index 4 and 5, they have 0, 0. So then what we would do, that if we keep a cell for brand number 1, we would earn 20. If we keep a cell for brand number 2, we would earn 13. If we keep a cell for brand number 3, we would earn 17. And we have only two cells. So which all we would select? We would select the two greatest. So we'd select 20 and 17. So my final answer should be 20 plus 17. So how do you get 20 plus 17 is when you sort this array. Okay, so this array has 20, 13, 17, 0, 0. When you sort them up in decreasing order, it becomes 20, 17, 13, 0, 0. After that, take the first n values. So n is 2 here, so we would take the first two values. So 20 plus 17 gives me 37. This would be my final answer. I hope it is clear to you. Okay, so this was my problem B. I think we can move to the next problem now. Okay, so let's move to problem C, where we have while rummaging through things in distant drawer, Anya found a beautiful string S consisting only of zeros and ones. Now she wants to make it even more beautiful by performing Q operations on it. Each operation is described by two integers I and V, and means that the ith character of the string is assigned value V, and the assignment Si equal to V is performed. Okay, so but Anya loves the number 1100. So after each query, she asks you to tell whether the substring this is present in her string or not. So basically what you are given is, initially you are given a string S, which is a binary string consisting of zeros and ones only. Then there are Q operation. In every operation, it's an updation operation. Basically, you are updating the index I to V. Okay, so if initially the index I was containing 0, now you are telling I comma 1, it means the index I is updated to 1. So this in every operation, there's an updation operation. After that, what is happening is, for every query you need to answer after that updation, whatever my string is, whether that string contains 1100 as a substring or not. You need to answer yes or no, whether it contains a substring 1100 anywhere or not. Okay. So if you look, okay, let's take the third test case and understand what we need to do. Okay, here initial string is given as this. Okay, it has indexes 1, 2, 3, 4, 5, 6. Now, we are given queries. In the first query, it's telling that update index I equal to 1. So update index 1 as 1. So it is telling S1 is equal to 1. So you need to update the index 1. It was 1 already. Now making it 1 would not affect your string. So my string would remain 1111010. That would be my string after this updation. Now here, do we have a 1100? That's what we need to check. In every query, we need to check whether we have a 1100 as a substring or not. Now, does it have a 11101101? Okay, it doesn't have a 1100. In this, you can see it doesn't have. So we would answer no. Now we would update index 5 as 0. So it has index 1, 2, 3, 4, 5, 6. Okay, so now this index 5 is updated to 0. Okay, so what it would become? So S5 is updated to 0. It would become 1110. It would be 0 now. So 0, 0. Now, does this string has a 1100 as a substring? We can see here we have 1100 as a substring. Okay, so we would say that yes, this string has 1100 as a substring. Okay, now then we are updating S4 as 1. Okay, so 1, 2, 3, fourth. The fourth index is updated to 1. So it becomes 111. This is updated to 100. Okay, so this is my new string now. Now for this string, does it have a 1100? We can see that it has a 1100 here. So we would answer yes to this query. Now we would update S5 as 0. So 1, 2, 3, 4, 5. This is the fifth index. This is updated to 0. It means it remains the same. So it is 1, 1, 1, 0, 0. It remains the same. And if it is same, then again it has a 1, 1, 0, 0 in it. So we would answer yes for that. Okay. So these would be my answers for the query, a no and a triple yes. You can see for this third query, we have no and triple yes. I think it is for the third query. For first query, we have 4, the first 4. Second query, we have 3, the next 3. And then from here, we have no and a triple yes. This is for the third test case. Okay, I think our answer was right. So this is what we need to do here. Now, how do you optimally check this? Okay, so if you go by the brute approach, what we are doing here, you have your initial string. At every query, you update an index. Okay, let's say you updated that index, you have the new string. In that, if you want to check whether 1100 is present or not, you just run a loop. You would check the first 4 characters, whether it is equal to 1100. It is not. Then you would check the next 4 characters. Okay, is it equal or not? Then the next 4 characters. That way we would go. Okay, so we would just run a sliding window of 4 characters and one by one check. Okay, so here you checked, it was a no. Then here you checked, it was a yes. So you returned a yes whenever you get a yes. So what would be its time complexity? So for every query, you are running this sliding window. So the length, if the length of the string is n, you are running this window n minus 3 times. So it's like order of n for every query. So overall, it would go q into n. For every query, you are running an order of n operation. Now, if you look at the constraints, q is 2 into 10 power 5 and size of the string is also 2 into 10 power 5. So q into n would be 10 to the power 10. So that won't be accepted, for sure. Okay, so this time complexity won't be accepted. So you need to optimize this. You need to find it in some better way. Okay, so what you can do is, how can you answer every query in not order of n but better time, maybe order of 1 only, or some constant time, or maybe log n at max. Okay, so what you can do is, for the initial string, the how many occurrences of 1100 is there. You can run a loop in your initial string and then calculate how many times you have 1100 in it. Okay, for the first 4 characters, it's not. Next 4 characters, next 4 characters. That way you can just check for 4 characters how many times it has the occurrence of this. Now, whenever you update an index, what is changing? Now here the number of occurrence of 1100 was 0. When you updated this index 1 to 1, okay, here there was like no change. So nothing was changing. It remained 0 only. Now, after this, when you updated this fifth index to 0, what happened? When this fifth index was updated to 0, then this substring, it became equal to 1100. So you have a 1100 now, which was not present before. So when an index is updated, what all substring do you need to recheck from before? Okay, so if initially there was no 1100 occurring here and one of the index is updated, so what all substrings are changing in this? Okay, so you were checking the first 4, the next 4, and then the next 4. Okay, so if you look this, okay, or if you look at the first 4 index, then the next 4, and then the next 4. These were the 3 substrings that you were checking in this. Now, when this index is updated, okay, if you check this substring, this is changing. If you check this substring, this is changing. But if you are checking this substring, the first substring, this one, the first 4 characters, this is the same as before because this index is getting updated. So you don't need to check this. Okay, you only need to check those substrings which are changing. Now, how many substrings would be changing? If you have a very long string of length n, okay, let's say you have a very long string of length n, and some index I, this index is updated. Okay, before maybe it was 0, it became 1, or it was 1, it became 0. Whatever is changing, if this particular index is getting updated. Now, in my initial string, I was checking the first four, the next four. These all substrings I was checking. Among them, what all substrings are there which may change after this updation? It would be the like this substring. Okay, what all would change? It would be this substring, this may change, or this substring may change, or this substring may change, or this substring may change. Because this, 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 and this. These are the only four substring that have this index. Now, if you go to the other substrings, this substring or this substring, they are not going to change because all the four characters in them remains the same. Okay, so basically what you need to do is whenever an index is updated, you only need to recheck these four substrings. If you just recheck these four substring, whether they were 1100 before and is not 1100 now, or it may be a case that it was not 1100 before, but it became 1100 now. There can only be two cases. So either if you are checking this string, either this was not 110 before and it became now, or it was 110 and it is not now, or maybe it was not, still it's not, or it was, still it is. Okay, so these are the only four cases. So we can just maintain an initial count variable. In that we would just have the count of total number of occurrences of 1100 substring, and then after every query, we would just recheck these four substring and update this count variable. And if this count is greater than 0, we would answer a yes, else we would answer a no. I hope this logic is clear to you. So what we would do is we only need to update the change. So in my initial array, I would maintain a count variable, count equal to 0, and I would run through this initial string all the substrings, whether they are equal to 1100 or not. If any one of them is equal, I would do a count plus plus there. And then for every query, what I would do is from my initial, how do I check these updations? Okay, one way is what I can do is if my ith index is updating, then for all these four strings, okay, before updating, what I would do, if among them any one of them was 1100, okay, then we'll decrease its count. Okay, we'll do count minus minus. If whichever, if one of them is equal to 1100, we would do count minus minus for the previous string. Then we would update our string, and then again for this new string, I would check for all these four strings. If one of them is equal, I do a count plus plus. Okay, so basically what I am doing, if what I'm doing is first deleting this index. So when I'm deleting this index, all those, if earlier I was having a 1100 anywhere, okay, if it was a 1100 here, okay, and it is getting updated to 1. So before updating, I would check if there was a 1100, then I do a count minus minus. Now it you'll assume that this index is deleted, so it is no more a 1100. So I'll do a count minus minus. If any one of them is, whichever is equal to 1100, I do a count minus minus for each one of them. And when this after that, I would update this index. So basically I'm adding this index here. Okay, first I deleted this index, then I'm adding this index. So by adding this index, if any one of them become equal to 1100, I do a count plus plus. Okay, so I'll remove, for that I'll do a count minus minus, then I would add, for that I will do a count plus plus. So that way my count would be updated. Now for the updated count, I would check if it is greater than 0, I answer a yes, otherwise a no. I hope this logic is clear to you. So we can move to the code. Okay, so what I'm doing, I took the input string as seen as, n is the size of the string. Now I took q as input. Okay, this input part is done. Then I'll take the q queries. So I would initially only calculate the count of occurrence of 1100. So my count variable is initialized to 0. Then I would run a loop from 0 till n minus 3. I would check if s dot substring. Okay, so the substring starting with I. Okay, this way I'm going to every possible substring of length 4 starting with 0. up till n minus 4. Okay. So if I'm at I equal to n minus 3, then my last index would not exist. It would have only of length 3. So I'm going up till n minus 4. So less than n minus 3. So s dot substring I comma 4, this would give me the substring from si plus 1, si plus 2, si plus 3, the first 4 length substring. If that is equal to 1100, I would do a count plus plus. Okay. So this is my initial state for the initial string. How many times I have the occurrence of 1100, that would be stored in my count variable. Okay. After that, in every query has I and V. It means SI should be updated to V. Now in my string, this is 0 based. In the queries, I is given as 1 base. So I did a I minus minus to convert it into 0 based index. Okay. So if I have I equal to 1, that means in 1 based, it is referring to S of 1. But here my string is 0 based. So I do a I minus minus so that I am referring to my 0 based index I. Okay. Then what I would do is, first of all, I would what all substrings do I have to check? I only have to check if this is an I. Okay, I have to check this one. Okay, what is this one? This index is I minus 1. This is I minus 2. This is I minus 3. Basically, from I minus 3, substring from I minus 3, substring from I minus 2, substring from I minus 1, and substring from I. Okay, so we run a loop from I minus 3 to I. Okay, so J is running from I minus 3 to less than I plus 1 or equal to I, you can say. So from I minus 3 to I am running a loop. And if that J, like I minus 3, that may become negative, I is 1. Okay, so we'll ignore if J is becomes negative or J plus 3 is greater than equal to N. Okay, so if any of these index is not valid, okay, if J is less than 0, or if we are taking a substring till J plus 3, so if that index is not there, then I do a continue just to check for invalid indexes. Now, if I have indexes from J up till J plus 3, then I take the substring from J for length 4. If that is equal to 1100, then I do a count minus minus. Okay, so what I'm doing, these strings I'm checking. If any of them is equal to 1100, then it is no more equal to 1100 because this ith index is deleted now. So I do a count minus minus. So first I deleted the ith index. I did count minus minus if any of them was 1100. Now I am adding the ith index with the new value. So SI is updated to V. Okay, so V was an integer. I converted it to a character using this. Okay, 0 character plus V. So my SI is updated now. For the new updated SI, I would check those four. Same thing that I wrote there. Okay, the same loop. Okay, same this condition. Okay, these all is copy pasted. Only for this case, if it is equal to 1100, I do a count plus plus instead of count minus minus. So this whole thing is same to same copied. Count minus minus is replaced with count plus plus. That's the only change. Okay. So after my ith index is updated, I do a count plus plus whenever I get a substring 1100. And then for the updated count, if this count is greater than 0, I do return a yes, otherwise I return a no. I hope this is clear to you. Okay. So if you look at the time complexity for this code, this n size string is taken as input. This loop is running order of n times. For every query, this is running from I minus 3 to I. Okay, this is running 4 times at max. Okay, this loop is running at max 4 times. This loop is also running at max 4 times. And this is a if else condition. So this all things is a constant time operation. 4 plus 4 plus 1 if else. Okay. 9, 10 is it's a constant time operation, not an order of n time operation. So a constant time operation q times. So this whole is order of q only. So overall, I can say my overall time complexity is going to be an order of n here and the order of q here. Okay. So order of n plus q. So not n into q, I did it in n plus q only. So this would be well accepted for the given constraints of n and s. Like s was 2 into 10 power 5, q was 2 into 10 power 5. So their sum would be accepted. Okay. I hope this is clear to you. The space complexity would also be like we have a string of size n, so it would be order of n. Is there any doubt in this problem, or we can move to the next problem now? Okay, let's move to the next problem, which is problem D. So here I love 1543. So Polycarp wake up and realize this is his favorite number. So first thing that Polycarp saw that day as soon as opening was a large wall carpet of size n by m cells. N and m are even numbers. Uh, each cell contains one of the digits from 0 to 9. Okay, so Polycarp became curious about how many times the number 1543 would appear in all layers of the carpet when traversed clockwise. Okay, what do you mean by layers? Okay, you can see if this is a grid of n cross m given to you, then your layers, this would be your first layer, this outer box. Okay, so if this is the carpet, then this is your first layer. Okay, this is your second layer. Okay, so this way you are dividing this carpet into layers and then you are traversing it clockwise direction. So while traveling in clockwise direction, if you ever get a 1543, if you get 1543 while traveling in clockwise direction, then you say like you just need to return the count of 1543. How many times are you getting 1543 in this? So like for this, if you look here, you got here you in the outer, in this outer layer, you can see here you got 1543. Okay, 1543. So this was a +1 to your answer. And then others you can analyze 1584. So like 1543 is only here in the outer layer. In the inner layer, if you talk about here, 1543 is here. If you move in clockwise direction like this, you get a 1543. Other than that, you don't have anything. So a +1 there. So a total of 2 would be your like answer for this test case. So likewise, you need to analyze every test case and find how many occurrences of 1543 is there in any of the layers. Just the sum of occurrences of 1543 for all the layers basically. So if you look like, you can look at other test cases. If you look at this test case, okay, let's take it there only. Okay, like you are given this test case, then this is your matrix or this is your n cross m grid. In that, you just divide it into layers. Okay, so this would be your first layer. This is would be your outer layer. This would be your second layer. Okay, after that it's finished. You have only 2 layers. Okay, now if you look at both the layers, do you get 1543? Okay, you just need to count how many times you're getting 1543. Here, if you look, okay, like this was the test case which was described here. Okay, it was the same test case. Okay, no, that was different. Okay, that was different. So this is of length 6 cross 4. Okay, so these are the layers. Now in this, how many times you have 1543? If you look at the, if you look at the first layer, what is the first layer? You have 5 4 3 2, then 2, then 2, then 2, then 2, then 2 1 2 3 4 5 6 times 2, 1 2 3 4 5 6 times 2, then 4 9 5 2 2 4 1. Okay, like you can just break this layer like this in this order: 5 4 3, then 6 times 2, 5 4 3, 6 times 2, then 4 9 5 2 2 4 1, 4 9 5 2 2 4 1. This way you can break it, and then you are moving clockwise. After 1 you move to 5 again. Okay, so you can consider this as a cyclic array. In this cyclic array, how many times you have 1 5 4 3? That's what you need to find out. Okay, so what all, so just take all the subs basically in the, like the last question, just take all the substring of length 4 or a sub arrays of length 4. So if you take the first 4 element 5 4 3 2, it's not equal to 1 5 4 3. Take the next 4. This is not 1 5 4 3. These are like not 1 5 4 3. Where would you get a 1 5 4 3? if you look here, you get a 1, then 5, 4, 3. Okay, so this is cyclic. After the last, you move to the first. Okay, so after 1, you move to 5. So 1, 5, 4, 3 was here. So you add a +1 to your answer for this 1, 5, 4, 3. Okay, now let's look at the next layer. So the next layer starts with 1. Okay, so if you look the next layer, this was our next layer. Okay, it starts with 1, then we move to 5. So 1, then we move to 5, then 4, 3, 0, 4, 3, 0, then a 1, then a 4, then a 3, then a 4, then a 5, and then we come back to 1. Okay, after that, cyclically we come back. So this is my second layer. For the second layer, how many times I have 1, 5, 4, 3? Here you can see we have 1, 5, 4, 3. Then no other 1, 5, 4, 3. Okay, this is the 1, 1, 5, 4, 3 that we have. 1, 5, 4, 3. Here you can see this was 1, 5, 4, 3. So you add a +1 to your answer. So a total 2 was your answer for this test case. For the last test case, your answer was 2. Okay, so what you need to do is, if you look at the constraints of the problem, n and m are up till 10 to the power 3. So if you just do a brute force approach, just extract every layer and then check whether that is how many times that has 1, 5, 4, 3. Now, in total, whatever layers you have, in total, the number of elements. Now, if there's a layer of length, let's say n, then in order of n, you can find how many times 1, 5, 4, 3 is occurring. So first of all, just break this down layer down into a vector of size n. Okay. So if you have a layer of size n, you get a vector of size n. In that, you can just one by one go to every subarray of size 4 and then one by one check. Okay, cyclically you would go. So in order of n, in order of the length of the layer, you can find how many times 1, 5, 4, 3 is occurring. And in total, if you sum up the length of all the layers, this layer plus this layer, total it would have n into m number of elements. Okay. So this length is n. You have a n cross m matrix. Okay. So your overall time complexity in n into m, you can find. Okay, so whatever the length of the outer layer plus the length of inner layer, all the layers combined, their length, combined length would be n into m. So in order of n into m, you can just find out this thing if you just break this layers down. And n and m are 10 to the power 3, so n into m would be well accepted. Okay, n into m doesn't cross 1 is 6 for all test cases. So you just need to do the brute force approach here. Just go to every layer and compute how many times 1, 5, 4, 3 is occurring. So how do you do that? Okay, so I'll show you in the code. So what I would do is whatever, okay, whatever matrix I have, okay, whenever I have a grid of n cross m, okay, let's say I have a grid of n cross m. Okay, so let's say I have a grid. This is of size m, and we are given that n and m are even integers. Okay, so this length and breadth, they would be even. So if you have an even length, so what would be the outermost layer? Okay, how would we traverse through the outermost layer? Okay, so if we are at the first layer, first we would travel this. Okay, so like if I'm indexing it with 0 based index, okay, this is 0, 1. That way we would go up till n minus 1. Okay, here how would I index it is I have 0, 1. That way I would go up till m minus 1. This would be m minus 2. So what I would do is for the first layer, I have to travel this. So one by one, I would travel to all the four parts. So first, this would be, I would keep I equal to 0 fixed. And for j, I would vary from 0 to m minus 1. Okay. So I equal to 0 fixed and j would vary from 0 to m minus 1. Okay. And then I would keep j equal to m minus 1 fixed and then I would traverse till here. Okay. So I would keep j equal to m minus 1 fixed. I would go from, okay, till here we have already done. So we would start from here and go up till here. And then this one would be covered in a single time. So I would be traversed from 1 to till here. This is n minus 2 to n minus 2. Then I would keep, for this, I would keep my I equal to n minus 1 constant and j would travel in the reverse direction from m minus 1 to 0. So I is kept as n minus 1 and j is going from m minus 1 to 0. And then to travel this part, I would do j equal to 0 is fixed. And then I would go from n minus 2 up till 1. Okay. This is the traversal for the outermost layer. Okay. We did that, let's say. Now, what about the second layer? Okay. What if we are in the second layer? So this was for the, you would say, layer 1, L1. Okay, let's move to the second layer. Let's see for the second layer what we have. For the second layer, I would start this for this thing. Okay, for this traversal, I equal to 1 is fixed. So I equal to 1 is fixed. J would go from 1 to m minus 2. Okay, this thing is done. After that, I would travel this. Okay, before that, till here only. Okay, then I would travel here. So basically, my J is fixed at m minus 2 and my I is going from 1, 2 or 2. I would start from here, from 2 to up till here, n minus 3. Okay, and then I would keep travel here. So my I is fixed to n minus 2 and my j would go from m minus 2 to 1. And then I would travel in this part. For that, my j would be fixed to 1. Okay, and I would travel from m n minus 3 to, okay, this point is n minus 3 and this point is 2. Okay, so this is for the second layer. Now, how many layers, first of all, how many layers would you have? Okay, when you are, like, if you see for this matrix, you had 1 layer and 2 layers. It was finished. So when are you finishing? Basically, if you look at the breadth, it has 4 elements. So this would be first layer, this would be second layer, and then next layer is not possible. Okay, so basically you have, if this is of length m, so you can have m minus m by 2 layers at max, and m is even. And for the length, same way, if you have a length of n, then here you would have a length of n, then n minus 2, and then here you can have, but due to this restriction, you were not able to have. Okay, so basically the minimum of n comma n, whatever that is, half of that. Okay, so either it would be n by 2 or m by 2, whichever is minimum. So I can say the number of layers would be the minimum of n comma m by 2. Okay, so I would say the number of layers is equal to minimum of n comma m by 2. Okay, so if you have got the number of layers, now how are you moving? For the first layer, these were the conditions. For the second layer, these were the condition. What would be the condition for the kth layer? Okay, so when you are starting from here for the first layer, from here for the second layer, For the third layer, we start from here. So always for the kth layer, I can say that you would start from k comma k. This would be your starting point, and then you would move. Okay, so this was for layer 1. This was for layer 2. What can we write in general for layer k? That for layer 1, you started with, okay, like in zero based indexing, I can write this as k minus 1 comma k minus 1. Okay. For the first layer, we start with 0 comma 0. So you will fix I equal to 0 and traverse from 0 to m minus 1. For the first layer, you fixed I equal to 1 and this way. Okay. This j changed from 0 to m minus 1 to 1 to m minus 2. Okay. Here, this was m minus 1. It changed to m minus 2. This I changed from I equal to 1 to n minus 2. It changed to 2 to n minus 3. Okay. So a plus 1 here, a minus 1 here. You went to the next layer. Same way, a minus 1 here, a plus 1 here. You went to m minus 2, 1. Minus 1 here, plus 1 here. N minus 3, 2. Okay. So basically, in general, you can say for layer K, I would say that I starts from K minus 1 and J would grow from K minus 1 to M minus 1 minus K. Like for layer 2, it was M minus 2. So up till M minus K, basically, you are going. Okay. So M minus 1 for first layer, M minus 2 for second layer, M minus 3, M minus K for. So likewise, you can find that in terms of K for the kth layer. This would be the first condition. You would start from you would fix I as K minus 1 and traverse from K minus 1 till M minus K. Okay. Then you would fix your J as M minus K. For the second layer, it was M minus 2. For the kth layer, it would be M minus K. And then I would be from 2 to N minus 3. So it would be from K minus 1 to, or from K to N minus K minus 1. Okay, so that would be the next. After that, the third, this one, I starts with N minus 2. So it is N minus K. I starts with N minus K. And J is moving from, it was M minus 2 to 1 for second layer. So for the kth layer, it would be M minus K to K minus 1. Okay. And then the next one would be for J equal to 1, you fix. So J is fixed to K minus 1 and I would travel from N minus 3 to 2 for the second layer. So N minus K minus 1 to 2, it means K. Okay, so this thing I can write for my kth layer. These would be my traversal. First, I would fix I as K minus 1, travel for J from K minus 1 to this. J is fixed here, this. So this way I would travel for the kth layer. So I would run a loop. I would run a loop from K equal to 1 up till minimum of N M by 2. So a loop would be run from this to this, and inside the loop, I would traverse this way. I would traverse and put all the values. Let's say in a vector, I would push all the values, and then in the that vector, I would check cyclically if there exists a 1 5 4 3. Okay, so that way I can just compute. Okay, let's look at the code. You will understand what I'm telling. So what I did here, I took the input, okay, a vector of string. Then I run my k from 0 to nm by 2. Okay, so I'm running my k. So I'm telling the first layer as layer 0. Okay, so here I was telling the first layer as layer 1. Here I'm telling the first layer as layer 0 and the second layer as layer 1 in my code. Okay, so it's 0 base. So wherever I have k, it would change to k minus 1. Okay, so whatever I have written here, all my k would change to k minus 1 in my code because I've taken 0 based layers in my code. Okay, k is running from 0 up till less than n comma m by 2, min of n comma m by 2. Okay, so I initialize my vector. This is vector of int. Okay, so I initialize a vector, and in that vector, I would just one by one push back. Okay, initially I'll fix. Okay, first I'll fix I equal to k minus 1. Okay, so I is fixed to, now k minus 1 would change to k here. Okay, because this is 0 based. So I is fixed as k here, and j would travel from k minus 1 to m minus k. That would change to k to m minus k plus minus 1. Okay, so k to m minus k less than its rep is less than m minus k. Okay, so j would run from k to less than m minus k, and in the vector I would push a of k comma j. So I is fixed to k and j is running from k minus from k to m minus k. So all these values, okay, minus 0 because this is a string, this would return a character. In that I'm doing minus 0 to get a integer. Okay, so this is a vector int. So that way I'm pushing back. Same for that. Here I have fixed my j as m minus k minus 1. Next I would fix my j as m minus k minus 1 because I've taken k as 0 based, and then running a loop for I equal to k plus 1 to n minus k. So I equal to k plus 1 to n minus k, like minus 2. That way I'll push back. Okay, same for the third. Here I would fix my j and run a loop for my I. Okay, I run a loop for my I and fixing my j. Okay, here this is the third one. I'll fix my I and I run a loop for j. I run a loop for j and fix my I as n minus k minus 1. Okay, here I fix my j as k and run a loop for my I. Okay, that way I'll just iterate through that whole basically that whole layer in clockwise direction. So I have traversed through the whole layer in clockwise direction and pushed those values in my vector vec. Now I need to check in my vec how many times I have an occurrence of 1543. So I'll take the size of vector as size and run a loop from I equal to 0 up till size. So I'm traversing through this whole vector with every index as a starting index and take a basically with that as starting index, I take a substring of length 4. Okay, so with I as starting, I'll travel from I up till I plus 3. Okay, up till less than I plus 4. Okay, so I'll travel from I up till I plus 3 and push those to my string. Okay, this way I'm creating a string of size 4. Okay, first it would be vec of j mod size. Why I'm doing, because if I'm at I equal to n minus 1, let's say. Okay, so if I'm at the last index of my vector, let's say here, you have a vector in 0 based indexing. Okay, I have traversed through the layer and extracted this layer. Now, when I'm starting with 7, after 7, I would go to 0, then 1, then 2. Okay, this way I would take my substring. So what I'm doing, I'm running a loop from I. So I'll start with 7. Okay, and then I'll have 7, 8, 9, 10. These are the indexes which I have to take. So I do a mod 7 in them. So when I do a mod 7, 8 would be like mod 8, sorry. The size is 8. Size of my vector is 8. So when I do a mod 8, so 8 would get converted to 0, 9 would get converted to 1, 10 would get converted to 2. So I'm traveling 0, 1, and 2 instead of 8, 9, 10. Okay. So 8, 9, in 8, 9, 10, if I do a mod with the size, then after 7, I get 0, 1, 2. Okay. So this way I'm cyclically traveling this vector. So I'm cyclically taking a substring of length 4 from I to I plus 4. I add that to my string, and if that string is equal to 1543, I would do answer plus plus. Okay, that way I do an answer plus plus. So every time I get a 1543, answer is going to get plus plus in slice with 0. I get my final answer. I hope this is clear to you. If there is any doubt, you can ask. No, this was a brute force only. You had to just implement that, but for implementing, you had to keep these in mind, how you would traverse an array uh, in clockwise direction, every layer. Okay, so implementing this was a good concept that you should know. It was implementation based problem only. Okay, so I hope this is clear. So if you look at the time complexity, this input part is order of n. I'm taking the input. Then this is running minimum of n or m times. Here, this is like these loops are running. Overall, this whole thing, as I showed you, overall what I'm doing, I'm traversing through every layer. So this whole thing overall is actually order of n into m. Okay, at max I'll go to every element once. Okay, so this whole thing is of the, like you can say, this combined is order of length of layer, I would say. This is the order of the length of the layer. Okay, which is order of size, I would say. Okay, this is order of size. Okay, size is the length of the layer, vector size. This whole thing is running order of size, and the sum of the sizes overall is n into m. Okay, that's what I'm telling. So for every loop, I'm running the size of the layer. I'm running a total complexity inside the loop is size of the layer, and the sum of the sizes of all the layers is n into m. Okay, so overall this is order of n into m, and I'm printing the answer. So my time complexity is order of n into m, and my space complexity would also be order of n into m. I'm using a array of size n into m, like a vector of string. Okay, the string is of size m, and n times we have that. I hope this problem is clear to everyone. So then we'll move to the next problem. Okay, so let's move to the next problem, which is problem E. Okay, conspiracy of ancient sages, this is this. Okay, there are n countries with exactly k regions. For the jth region, the ith country, the calculated value aij, which reflects the amount of water in it. And what is happening here is basically we are given some array A. What it represent is for the ith country and jth region, what is the amount of water in it. After that, something is happening, and we are creating an array B according to something. So what that array B is, Bij is equivalent to A1j or A2j or up till Aij. Okay, so for the in the array B, what I'm doing for the jth column, I'm taking the bitwise or of every, like A1j, A2j up till Aij. So I'm taking a bitwise or for that, basically a prefix, or you can say for that column. Okay, that's how you create an array B. After this array B is created, after redistribution of water, they would send you Q queries. Okay, in every query, it contains M requirements. Okay, so the requirements are of this type. Okay, so the requirement are of this type, that you are given an R, O, and C. Okay, so if O is a character, either it would be less than symbol or a greater than symbol. So if it is a less than symbol, it means the rth region of the country you choose, the new value must be strictly less than the limit C. So if you are given, okay, and if it is greater than, it should be strictly greater. So these type of M requirements are there, and then you need to find that then you need to find a suitable country you choose which satisfies all these requirements. If there are multiple, you need to output the smallest one. If there is no such country, output -1. Okay, so I'll explain you the question with the test case. Okay, let's say you are given this. What does it mean? First of all, you have this is n, m. Okay, so you have this, you can say a matrix of size n cross m, or not n m, it is n and k and then q queries. Okay, so this is not m, this is k. And then you have 4 queries. So first let's look at this. Okay, first of all, what is given to you is initially you are given this. Okay, that you have n countries. Okay, and for every country there are k regions. Okay, so this matrix denote that for like country one, for the first country you have the regions as 1, 3, 5, 9. Like this is region number 1, 2, 3, 4. Okay, for country 2 you have 4, 6, 5, 3. For country 3 you have 2, 1, 2, 7. Okay, so this is the initial condition that is given to you. This is your initial array A, that what it represents, that for country 1, in the first region you have 1 as some water, in second region you have 3, in third region you have 5, in fourth region you have 9. For country 2 you have 4, 6, 5, 3. Likewise for country 3, this. Now this is your array A. Now when you convert to array B, what is happening is you are given Bij is equivalent to A1j or A2j or A3j up till Aij. Okay, so Bij is this. What does that mean? Okay, if you want to compute, let's say this B of 3 comma 2, it means that B of 3 comma 2 is A of 1 comma 2, 1 comma j, 2 comma j, 3. This or this or this. Okay, what is B of this? It would be this or this. Okay, so basically when you're converting to array B, what you are doing is for any element, you are taking the prefix or for that, basically that column. Okay, so for column 1, the first row would remain the same. For the second row, you would take the or, you would take 4 or 1. Okay, so for the second row, it would be transformed to this. That way you would take the or of these elements, that would be here. Okay, for the next row, this would be the or of all 3 elements. Okay, this value would be the or of all 3 elements, this value would be the or of all 3 elements. So that way you are like taking the prefix or for every column. So this array A would get converted to array B like this. Okay, so when you create this array B, so in 1, 2, 3, you have these 3 countries and regions are 1, 2, 3, 4. Okay, so the first row for this you take or with previous, like you don't have anything. So the first row would remain the same, 1, 3, 5, 9. So the first country would be 1, 3, 5, 9 only. And then here, here you take the or with this. So it would be 1 or 4. Okay, so this would become 1 or 4. This would become 3 or 6. This would become 5 or 5. This would become 9 or 3. Okay, and then for this third index, it is the or of all the 3. So 1, 4, 2, 1 or 4 or 2. Okay, so 3, 6, 1 and 2, 7. 3, 6, 1. It would be 5 or 5, comma, or 2, and then 7 here. So 9 or 3 or 7. Okay, this is what your array B becomes. And if you look at the values of that, if you see, this was your array A and this is your array B. Okay, I think this is the first test case. Yeah, the first test case only. So it is basically this, you can say. Okay, 1, 3, 5, 9. Okay, it is basically 1, 3, 5, 9. Then it becomes 5, 7, 5, 11. So 1 or 4 is 5, 3 or 6 is 7, 5 or 5 is 0, 9 or 3 is, okay, 5 or 5 is 5 only, sorry. 9 or 3 is 11. Okay, and here you have 7, 7, 7, 15. 77750. Okay, this is what your array B becomes. Okay, now you need to answer the queries according to this array B. This is country 1, this is country 2, this is country 3, this is region 1, region 2, region 3, region 4. Now, according to this array, you need to answer the queries. Now, what you need to do in the queries? The first, like in every query, you are given an M and then M conditions. Okay, so you are given 3, so you are given 3 conditions. What does those 3 conditions mean? 1 greater than symbol and 4. It means that you need to select a country which should satisfy this condition, that for the first reason, the value should be greater than 4, strictly greater than 4. For the second reason, the value should be strictly less than 8. For the first reason, the value should be strictly less than 6. Okay, so your conditions are that whatever region you select, let's say whatever country you select, let's say you selected country number 2. Okay, so if let's say you are selecting the country number 2, this country should satisfy these conditions, that region 1 should have value greater than 4. Okay, this is region 1, its value is 5, which is greater than 4. So this is satisfied in this country. Okay, region 2 should have value less than 8. If you look at the region 2, its value is 7, which is less than 8. So this is satisfied. Region 1 should have value less than 6. Now region 1 has a value of 5, which is less than 6. So this is also satisfied. Now, so basically, if you're correct selecting country number 2 is satisfying all these conditions. Now, it may be possible that country number 1 is also satisfying all these conditions. Then you need to answer the country with the lowest number, the first country. So 1 would be your answer if it is satisfying. Now, in this case, if you check for country number 1, okay, let's say you assume country number 1 is your answer. Okay, then you check the conditions. The first condition is region 1 should have value greater than 4. Region 1 has value 1, which is not greater than 4. So it is not satisfying this condition. So I would say this country 1 is not satisfying the condition. So the lowest country that satisfies the condition is 2. So for this query, I would answer 2. Okay, like in the first query, you can see my answer was 2. Okay, same way you need to answer. For the second query, like any country satisfying that region 1 should have value less than 8, region 2 should have value greater than 8. Okay, so region 1, all the countries have value less than 8. For region 2, it should have value greater than 8. None of the countries have value greater than 8 in region 2. So this set condition is not satisfied by any of the country. So these combined are not satisfied by any of the country, would return -1 as your answer if the conditions are not satisfied by any of the countries. Okay, that way you have to answer the queries. Okay, so let's find out how would you solve this problem. So the first thing that you need to notice is when you are converting from array A to array B, what you are doing, any element Bij, what is, okay, so for the ith country, if you are looking at Bij, that is actually the prefix or of that whole column. Okay, what is this Bij? Prefix or of that whole column. What is this prefix or of that whole column? So I can write that Bij, which was, okay, it was this, Bij was this. That can be written as up till here. Okay, if I do till Aij minus Ai minus 1j. Okay, so till here that can be written as Bi minus 1j. Okay, what is Bi minus 1j? Is the prefix or up till I minus 1 for the jth column. So Bij can be written as Bi minus 1j or with Aij. Okay, this you can write. Okay, basically how you do prefix or, that's how you do that. Bij is Bi minus 1j or with Aij. Now what you can say with this, you know the property of OR, that whenever you do an OR of two numbers, X or Y, the result that you get, it is greater than equal to both X as well as I. Okay, do you know the property of this OR? Okay, if you don't know, then whenever you do an OR of two numbers, what happens? Some of the bits get set. So if X has some of the bits set, then making an OR with Y is not going to reduce its value for sure. It's going to be greater than equal to X. Same for Y. Its value is not going to be reduced. So whenever you do an OR of two numbers, it is greater than both the numbers, that is for sure. So whenever you are doing an OR, so whatever value was there at bi minus 1j, if you are doing OR with some positive number aij, that means this bij is going to be greater than equal to this bij. From this we can conclude that this total value is going to be greater than equal to bi minus 1j. Okay, because this is greater than both this and this. So I can say that this value is greater than this value. So I can say that bij is greater than bi minus 1j always. It means that for any column, if I'm saying bij, it is greater than bi minus 1j, greater than equal to. That means whenever I'm moving down, it is going to be in increasing order. Okay. So whenever I'm moving down, you can see for when B is constructed, this is an increasing order. This is an increasing order, increasing order, increasing order. So, and I have proved that why it would be. So with this, you can just prove that always for every column, whenever you are moving down, it would be in increasing order only, because you are doing a prefix or. This has or till here. In that you are adding something extra. So that would increase its value only. So for every region, whenever you are moving to a lower country, its value is increasing. Whenever you are moving to a lower country, its value is increasing. Now, once you know that this is monotonically increasing, so what you can do is you can do a binary search in every query. Okay, as someone has written, can we do a binary search of every query? Yes, you can do. So through binary search, you can find the condition. So what exactly I'm doing here is basically I'm just taking upper bound or lower bound function. So whenever you have your condition is for region 1, the great value should be greater than 4. Okay, so if you have this condition 1 greater 4, okay, so it means for region 1, in region 1 you would find what all values are greater than 4. So in this, if you take the upper bound, okay, either you do a binary search or use the upper bound function directly. In login time, you can find the value just greater than 4. It is 5. So all the regions below it are valid, but all the regions before this are invalid. So like all the countries. Okay, so if you have a greater than symbol, so whenever you have a greater than symbol, what you do is you take the upper bound of C in the region R. Okay, so if you take upper bound C for basically region R, for okay, for okay, so if you have initially only computed that for region 1, these are the my values. For region 2, these are my values. For region 3, these are my values. Now in the region 1, in the basically you have a sorted vector in region 1. In that sorted vector, you apply the upper bound function and find the first value which is greater than C. Okay, here you found the first value greater than C was 5. So you can say that all the countries below 2 are valid. Okay, so I would say initially with, if there is no condition, all the countries from 1 to n are valid. Okay, so the range of valid countries, I can keep a range of countries that are valid, which would be initially from 1 to n. All the countries are valid. Then after the first condition, if the value should be strictly greater than 4 for region 1, so I took the upper bound, I found for this region, the value is strictly greater than 4. So all the regions below this is valid, but all the regions above that gets rejected. Okay, so initially my range was this, all the countries are valid. Now my range get reduced to this much only. This region gets rejected. Okay, after that I have this condition of 2 less than 8. Okay, so basically for region number 2, okay, 2 less than 8. That it means for region number 2, value should be strictly less than 8. Okay, so I analyze the region number 2. Okay, so I would apply in this, I can just apply the value just less than 8. Okay, the value just less than 8 is 7. Okay, and we can see that all the values are less than 8. So this condition is satisfied by all of them. So this was my valid countries. Among them, my basically through binary search, I found a value just less than 8. It was 7. So I would say all the values greater than this, they get rejected. So above 7, there was no value, so nothing get rejected. My upper bound of my range remains the same. So my range remains the same. Both country 2 and 3 satisfies this condition. After that, I have my third condition, 1 less than 6. Okay, so when I have the third condition, then I'll say that for region 1, the value should be strictly less than 6. So strictly less than 6, the first value is 5. So all those values greater than 6, like this region, they get rejected. So this much region is valid. Before that, all the region gets rejected. So my range, which was this initially, this region gets rejected. So my range is gets reduced to this only. Okay. So this way, what I will do, finally, after all the conditions are satisfied, if my range is not empty, then I would answer the lower limit of my range. If my range is empty, I would answer -1. Okay. So how I am maintaining my range is through a variable L comma R. Okay. So L comma R is my range. L is the lower limit. R is the upper limit of the range of countries that satisfies my conditions. So initially I will initialize L as 1 and R as N. Okay, so in my initial range is up till 1 to N. The whole range is satisfying my condition. Okay, and whenever I get a greater than symbol, okay, that it should be that the value should be strictly greater than, it means all those values which are less than equal to C, that is unsatisfied. Okay, so if we have some increasing values, so whenever you have some increasing values, and let's say this is your the value just greater than C, this is the first value greater than C, then all those values above would be greater than C, but all those values below gets rejected. That means I have to update my lower limit. Okay, so if my lower limit was L was here and R was here, the complete range was satisfying. Now I have to reduce my range till here. So this L gets updated to this. Okay, so whenever I have a greater sign, I would just remove this range. It means I'll update my L as, okay, initially if my L was already here and this range is satisfying, then no need to change the L. So it should be the maximum. Okay, so this was let's say 1 and this was N. Okay, so if this is some value just greater than with the upper bound, whatever value you got, so you need to update your L to that. So L is updated as max of L comma, whatever you got with the upper bound. Okay. So whatever you got with the upper bound, you will take the maximum. Okay. So your lower limit would get increased. Okay. So this whole range gets rejected. So your L gets updated to here. Okay. This range gets rejected. Now this is your L2R range, which is satisfying all the conditions. After that, if you get a less than condition, that means you would find some value which is just less than C. Okay, so there you would, okay, this L is updated till here. Okay, with a less than condition, you would find some value which is, let's say, strictly less than C, whatever C is given to you. Okay, so the greatest value which is less than C. So all these values before that, they all would be less than C. They are valid, but all these values, they are greater than equal to C. So these are invalid. Okay, so invalid. So whenever you have a less than sign, then you are going to update your R. Okay, so your R should reach here so that this range gets rejected. Okay, so in order to reject that range, your R should update to min of R comma whatever you get from the binary search just less than that value. Okay, now To get just strictly greater than, you use upper bound function. Okay, so here what you are using is you are using an upper bound of C for the rth column, and to get just less than, for that you would use lower bound. Lower bound return just greater than equal to. In that, if you do a -1, you get just the element just less than. So you can use a lower bound of C -1. Okay, this way you get the element just less than, and the element just greater than is the upper bound of C. Okay, so this value would be calculated, and you take the max with L. This value is calculated, you take the min with R. Finally, if in the final range your L is greater than R, your lower limit is greater than upper limit, you return -1. It means your range is null or 5. Okay, you don't have anything in your range. And uh, otherwise you print L as your answer. Okay, I hope this logic is clear. Yeah, we are doing the intersection thing only. Okay, so your initial range is from L to R, and then you're taking the intersection of the next range. Basically, you are updating L and R. So you are, for the intersection, you take L as max of L comma the new lower limit, and for R you take min of R comma the new upper limit. Okay, so with a greater conditions, you get a new lower limit. With a less condition, you get a new upper limit. So this way you are updating your L and R. Okay, I hope this logic is clear to you, so we can look at the code now. Okay, so we have N, K, and Q as input, and then we have K. Okay, so one thing is here, this initial array A that I have. Okay, that in general you take A of ij. Okay, this way you take. So that would contain, then your AI contains the whole row. So in A1, you have the whole row. In A2, you have the next row. In A3, you have the next row. And then maybe for B, you take the OR with the previous. So first you keep the first row same. Second row, you take the OR with the previous row. For the third row, you take the OR with the previous row. That way you can compute your B. But when you want to apply a binary search here, then you are applying a binary search on the rth column. Okay, you are applying the binary search on the first column or the second column or the third column. So if the column number, this J, is taken as secondary, then with your B, okay, if you have BI, that represents the ith row. Okay, now if you want to get the jth column, that is represented by B of 0j, B of 1j. Okay, likewise, that represents your jth column. So you cannot like write bj and get directly that whole vector. So what I'm doing is, instead, so for applying the binary search, you need this column only. Okay, you don't need like one by one. If you're going to every element of this column, then that would take order of n complexity and the number of rows. Okay, so that won't be efficient in because you want to do it in log n time. Okay, that's why you were applying binary search. If you do it in O of n time for q queries, that would like m conditions, so it would take m into n with the given constraints. Okay, if you look at the constraints, m was up till 10 to the power 5, and you have q queries which is up till 10 to the power 5, and the sum of m across all queries doesn't exceed 10 to the power 5. N into k doesn't exceed 10 to the power 5. Okay, so like for every query, if you're there is some m. Okay, and for every m, if you're doing an order of n thing, then this sum of m is 10 to the power 5. You are multiplying an order of n which is 10 to the power 5. That would go 10 to the power 10. So you need to answer every query in every basically condition. Every condition should be answered in order of log n, time only. So then it would be m into log n. Okay, sum of m into log n. Otherwise, it's sum of m into n if for every query you are going to every row. Okay, then there was no use of binary search. You can just linearly only go and do it. So for every basically condition, we won't recreate this. Array. What we would do is, instead of storing it as bij, I would store it at bji. Okay, I'll store the array as, in general, we store at aij, where I is the country number, but I would keep the array as aji. That way, the column number would be my primary. So that way, with aj, aj represents my whole column j. Okay, so I can apply binary search on aj. Directly on aj, I don't need to calculate like bj. We would compute bj from that. Okay, so instead of taking as aij, I'm taking aji, where j represents my column number. Column here is my region. Okay, j represents my region and I represents my country. Okay, this way I'm taking, so that I can have I can access aj, which is the whole uh, region j. Okay, which is the all countries in region j is accessible to me. Okay, so that's why I'm you can see I'm initializing as k cross n, not n cross k. Okay, k is the number of regions, n is the number of countries. Okay, and then I'm running a loop. Now this input part is for the I equal to 1 for the first country, I get everything for the second country. So there I have to run an outer loop of I from 0 to n and either loop of j from 0 to k, but I'll take scene of a of ji. Okay, so that way I'm storing. After that, I have to compute my b. Okay, so like instead of computing b, a is only converted to b is what I'm doing. So for every column, okay, I'm moving for every column from 0 to k. I'm running a loop from I equal to 1 to n. I'm doing a of ji or with a of ji minus 1. Okay, that's how I was computing my array b, right? So my array b was b of ij. B of ij was b of I minus 1j or a of ij. Okay, so what I'm doing is, whatever I have at a of ij, I do an or with a of I minus 1j, like because I minus 1j is already computed, it's already converted to b of I minus 1j. So what I'm doing is just a of ij or equal to a of I minus 1j. Okay, this is what I'm doing. A of ij, a of ji or equal to a of j I minus 1. Okay, this way my prefix or is taken for the ith row. Okay, so all for ith row, I'm taking a prefix or with the I minus 1th row. Okay, this is done. Now I would answer my every queries. So for the Q queries, I take M as input. Now this is my range from low to high. Okay, the L and R that I was taking, this is my range from low to high. Okay, low is the lower limit, high is the upper limit. So initial, my lower limit is 0, upper limit is n minus 1. Okay, so there I was taking a 1 based indexing, so it was from 1 to n. Here I'm having a 0 based indexing. This array is having a 0 based index. So I'm assuming as country number 0 to country number n minus 1 in 0 based index. Okay, so my range is from 0 to n minus 1 while m minus minus. So the number of conditions that I have, every condition is of type ROC. Okay, R and C are two integers, which denotes for the rth row, the condition should be either if O is less than, so strictly less than C, otherwise strictly greater than C. So I'm doing R minus minus because again, R is the row number in 1 based indexing. I convert it to 0 based indexing by doing R minus minus. So because my array A has everything in 0 based indexing. Now I would apply for less than, for strictly less than, what I told, strictly less than means lower bound -1. Okay, so I take the lower bound for array AR. Okay, for the rth column. Okay, R is my region number. So for the rth column, AR is my rth column. In that, I'm applying binary search. All is just AR dot begin, AR dot end. Okay, so in AR dot begin, comma AR dot end. In the rth column, I'm applying binary search, like the low, I'm taking lower bound. So greater than equal to C. This is what lower bound is going to return. Minus AR dot begin, I got the index because this returns an iterator. When I do AR dot begin, subtract from that, I'll get the index of the first value just greater than equal to C. So if I is the first value just greater than equal to C, okay, just greater than equal to C is returned here, then I -1 would be the value just less than C. So I take high as min of high comma I -1. Okay, so as I told you, for upper limit, how I am updating is, if I have a less than symbol, R is updated as min of R comma lower bound -1. So min of high comma I -1. Now, if it is a greater than symbol, then I take the upper bound of C for the rth row. Okay, so this would give me just strictly greater than C. So I don't need to do a -1 here. I would only be taking. So low as max of low comma I. So what I was doing here, L as max of L comma the upper bound, which is I. Okay, this way I'm updating my high and low. After all the conditions are done, if my low is greater than high, it means my finally I have an empty set, or my intersection returns in 5. So I don't have any valid country. Then I would see out -1. Otherwise, I would see out low +1, because low is in 0 based indexing. My country number is from 0 to n -1. Final output should be given in 1 based. So I'm just adding a +1 to convert into 1 based indexing to see out my answer. Okay. So this is what I'm doing. And this is the code. I hope it is understood to you. If there is any doubt, you can ask. If you look at its time complexity, this input part is n cross k. This again, this loop is running k into n times. Okay, this is n into k. For every query, okay, this m times, this lower bound is running log, like log n times. This lower bound is also running log n times. Okay, so a log n here inside m. So this in total is running order of m into log n times. Okay, so m into log n, for every query in total, it becomes order of sum of m, whatever you get, into log n. Okay, so I can write it as q into m into log n, but I'm given the condition that sum of m for all queries is 1e5. Okay, so overall it is sum of m for all queries into log n. This is my overall time complexity, and initial pre-computation is n into k. So I can say my overall time complexity would be order of n into k is initial input and pre-computation, then sum of m into log n. Okay, sum of n is 1e5, log n would be some 20, 30. Okay, so this thing is well accepted. My space complexity would be, I have a vector of size n cross k, so it would be n cross k only. Okay, I hope this problem is clear to you. The main thing was understanding that after taking that prefix or, it's an increasing function. In that, you can take upper bound and lower bound functions to apply, like you can apply a binary search. So you can take upper bound and lower bound, because these are strictly increasing functions, and compute the conditions. Okay, so those conditions are taken as a range from L to R. Whenever you have greater than, then some range is reducing, less than, then some R is updating. That way you are updating the ranges. Okay, when all the conditions are met, you take the intersection of all the conditions basically. Okay, so I hope this problem is clear to you. If there is any doubt, you can ask, or we'll move to the next problem. Okay, let's move to the next problem, which is problem F. Sorry, factor 3000. Alice has been gifting gifts to Bob for so many years, this, that. Okay, so I'll tell you what the question is. Basically, Bob considers a positive integer x to be interesting if it satisfies this condition. What does this condition means? That x, when expressed as k, in x when expressed as modulo 2 to the power I, it's not equivalent to k in modulo 2 to the power I. Then we would say that x is interesting. Okay. And what it does, basically what you need to do is just compute the XOR of all interesting integers in the range L to R. This is the definition of an interesting integer, and you need to compute the XOR of all interesting integers in the range L to R. So you are given L, R, I, and K. Now you have t test cases, so 1 in 4 test cases, and in every test case you are just given L, R, I, and K. Okay, so for every test case you can say a maximum of 1 in 4 time, 1 in 4 operations. Like there are 1 in 4 test cases already, so you cannot go L and R all up to 10 to the power 18. So obviously, you need to find something in order of 1 or order of log n type of thing. Okay, 10 to the power 18, if you're going in order of L or order of R, that won't be accepted. Okay, so you need to calculate this thing in a single formula or something in very optimized way. Okay, and you have something like 2 to the power things. You have bitwise XORs. So you can go in to every bit and calculate something. So it may be an order of 30 or order of 60 kind of thing can also happen. So these are some hints from the, you can say, or some obvious things, observations from the constraints. Okay, now how do you find that? So let's see, what you need to do is you have an L, R, I, and K. Okay, so you are given a L, a R, a I, a K. So you just need to find for the range from L to R, for all the numbers in the range of L to R, whichever number is a beautiful number, take their XOR. Okay, so XOR of all the beautiful numbers in the range of L to R. So you need to find XOR of all beautiful numbers in the range from L to R. That's what you need to find. Okay, what's the definition of beautiful? Definition of beautiful is that a number x is called beautiful if x modulo 2 to the power I is equal to k. That's what the condition is. Okay, if you mod it with 2 to the power I, like it's not equal to k. That's the condition for beautiful. Okay, you are given an I and a k which are fixed, a constant. So any number whose modulo 2 to the power I is not equal to k, that is a beautiful number. So one thing is, now if you look, you need to find XOR of all beautiful numbers. So if you are saying this, if x satisfies this condition is not equal to k, then it is a beautiful number. So if you find, like you can see that if it is not equal to k, there would be many numbers that are not equal to k. But if the condition was x modulo 2 to the power I equal to k, there would be some few numbers, some less amount of numbers that would satisfy this condition, maybe. Okay, so maybe finding this thing is easier. So what you can do is, in XOR, if you want to compute the XOR of, let's say, from L to R. Okay, for this test case, let's analyze this test case. What was the condition? Okay, you have L and R as 1 and 3. So among 1, 2, 3, how many numbers are beautiful? Where I is given as 1, k is given as 0. So if you take x equal to 1, okay, so 1 modulo 2 to the power I is, okay, 2 to the power 1 is 2, it is 1, which is not equal to 0, which is not equal to k. So it satisfies the condition. x equal to 2. So 1 is a beautiful number. So 2 modulo 2 to the power 1 is 2. It gives 0, which is equal to 0. So it is not a beautiful number. Okay, I hope you understand. For x equal to 3, we have 3, 3 modulo 2 to the power 1. Okay, which is going to give you 1, which is not equal to 0. So it is a beautiful number again. Okay, so here you can see x equal to 1 and x equal to 3 were beautiful number. Your final answer was 1 XOR 3, which is giving you 2. So 2 was your final answer for the first test case. You can see 2 was your final answer. Okay, you can see 1 and 3 are beautiful numbers. Their XOR is 2. So what I'm telling is, instead of, okay, the first thing is you need to do a XOR of all beautiful numbers from L to R. So what you can do is, you are doing, if you are doing XOR of 1 and 3, that's same as you do a XOR of all the numbers, and from that remove the XOR of non-beautiful numbers. That can is also equivalent to that. So if you do a XOR, if you can somehow find out the XOR of all the numbers from the range L to R, and from that, since I'm telling that these numbers are less, the amount of numbers which are not beautiful are less, so we would try to compute only the XOR of those numbers. And that, if you know the property of XOR, that if you want to remove something from, then XOR of like x XOR x is 0. It means inverse of XOR is XOR only. So if you take the XOR of all the three numbers, 1 XOR 2 XOR 3, from that, if you want to compute 1 XOR 2, you want to remove 2, what you can do is take a XOR of 2 in that. Okay, if in this, if you take a XOR of 2, you would get 2 XOR 2 would cancel out each other, you would get 1 XOR 3. Okay, so if you know this property of XOR, that means what you can do is compute the XOR of all numbers from L to R, and that from that do a XOR of all non-beautiful numbers. From that, if you do a XOR of non-beautiful numbers in the range from L to R, that is also equivalent to your answer. Okay. So we'll try to do this. So instead of finding a XOR of beautiful numbers, we'll try to find the XOR of non-beautiful numbers. Okay, this is one thing. And one more thing is, we need to, if my question was to find the XOR of all beautiful numbers from L to R. Okay, so like for that, I would need to do a XOR of all numbers from L to R. So whenever you have something from the range L to R you want to do, then you can reduce that question to, since you know the inverse of XOR, so you can reduce your basically whatever your question was from L to R. So your answer for L to R can be, if you can compute a function f of R, I'm denoting as this function returns the XOR, basically the XOR of all beautiful numbers from 1 to R. Okay, so I'm telling that f of n is XOR of all numbers, all beautiful numbers from 1 to n. Okay, this is what I'm telling f of n is. So when you want to compute the XOR from the range L to R, you can write that as f of R XOR f of L minus 1. Okay, so f of R is XOR of all beautiful numbers from the range 1 to n or 0 to n, whatever you want to write. Okay, so from starting from 0 only till n, take the whatever numbers are beautiful, take the XOR. From that, all the numbers which were less than L, you have to remove them. So take the XOR of f of L minus 1. So all the numbers less than n, their XOR, if you remove them, okay, if you take that inverse, that would be a final answer. Okay, so basically my answer from L to R, my final answer is f of R minus f of L minus 1. So if you can compute this function, you are done. Okay, if you can just find out this function, if you can somehow calculate this function, XOR of all beautiful numbers from 0 to n, then you can use this property to get your final answer. XOR from the range L to R can be obtained easily. Now, how do you compute this f of n? Okay, so f of n can again be written as, I need to calculate the XOR of all beautiful numbers from 0 to n. And as I said, that can be written as XOR of all numbers from 0 to n, XOR with non-beautiful numbers. So f of n is XOR from 0 to n. Okay, XOR of all numbers from 0 to n, XOR with XOR of non-beautiful numbers from 0 to n. Okay, f of n is this thing. Now, okay, now we'll see how can we calculate this. But if you want to compute the XOR from all the numbers from 0 to n, can you do this in some order of 1? If you know, like this is a very, you can say a standard question or whatever you want to say. If you just think a little, what would be the XOR of all the numbers from 0 to n? Okay, let's try to find this out. Can you calculate this fast? Okay, one way is taking the XOR from 0, XOR 1, XOR 2, XOR 3, one by one XOR till n. That would take order of n. Obviously, you don't, n can go up till 10 to the power 18, so you don't want to go till there. You want to compute this fast. Okay, and then this we will think how can we compute this. So how can you compute this fast is XOR of all numbers from 0 till 0 is 0. Okay, in that if you take a XOR of 1, okay, 0 XOR 1 would be 1. In that you do a XOR of 2. Okay, so 1 XOR 2 is 3, you know, that would be 3. In that if you XOR 3, okay, so XOR of all numbers from 1 to 3, what is that? So 1 and 2, you know, that XORs to 3. So 3 XOR 3 is 0. In that if you XOR 4, 0 XOR 4 is 4. In that if you XOR 5, okay, 4 XOR 5, what is 4 XOR 5? 4 is 100, 5 is 101. Their XOR would be 001. So you get a 1. 6, 1 XOR 6, okay, 6 is 110, 1 is 1. Their XOR would be 7. 7 XOR 7 would give you 0. 0 XOR 8 would give you 8. 8 XOR 9 would again, 8 is 1000, 9 is this. Their XOR would give you 1. You get a 1 again. Now, can you notice some pattern here? 0, it was 0. Again, we got a next 0 at 3. Next 0 at 7. Next 0. Where would you get the next 0? Okay, if you look 3, then 7, then, okay, let's write more. For 10, 1 XOR 10, you would get 11. 11 XOR 11, you would get a 0. XOR with 12, you would get a 12. Okay, so if you look at zeros, at 3 you got a 0, at 7 you got a 0, at 11 you got a 0. So every time at steps of 4 you are getting 0. Okay, so is it some kind of pattern? Let's see more. Okay, so whenever you have, what is 3, 7, 11? What is common between 3, 7, 11? Is that when you take modulo 4, you get 3. Okay, for this also modulo 4 would give you 3, modulo 4 would give you 3, modulo 4 would give you 3. So if you do a mod 4 with x and you are getting 3, then your answer is 0. And if you go to the just next number, 0 XOR with any number would give you that number. 0 XOR with any number would give you that number. 0 XOR with any number would give you that number. So for the multiples of 4, for 4 you get a 4, for 8 you get a 8, for 12 you get a 12. Okay, so if modulo 4 was 3, I'm telling you get a 0. If modulo 4 is 0, that means it's a multiple. You get n as your answer. Okay, now once for 4 you get n as your answer. Okay, when you do a XOR with 5, okay, so if there is a n which is a multiple of 4, if with that, if you XOR with n plus 1, so a multiple of 4, it would have some numbers and the last bit would be 0 for that because it's an even number. Any multiple of 4 is an even. And what would be n plus 1? It would have the same bits till here and a 1 here. Okay, so whenever you have a n would be like this, n plus 1 would be like this. So whenever we take the XOR of these two numbers, it would be this n plus 1 only. Okay, these like 1 only. These all numbers would cancel out and become 0. This XOR would become 1. So this would result in 1. So n XOR with n plus 1 would always result in 1 if n is an even number. Okay, that, like you can say this is a property only, that whenever you have an even number, you take XOR with n plus 1. Only this first bit is going to get flipped, rest remains the same. Their XOR would be 0, this XOR would be 1. So when for 5 your answer is 1, for 9 your answer is 1, for 1 your answer is 1. Okay, so here I can write, if my modulo 4 is 1, my answer is going to be 1. Now what is remaining? Modulo 4 as 2. So if you look at this 2, my answer was 3. For 6, my answer was 7. For 10, my answer was 11. So it's n plus 1. You can see that for modulo, whenever you had a 1 here, okay, n plus 1, for n plus 1, you had a 1. If you XOR with n plus 2, then you can see that this n plus 2 would also be an even number. Okay, so if you take n plus 2, that would also be some even number with last bit 0. If you XOR with 1, okay, this last bit would get set, it would become n plus 1. Okay, so when your modulo 4 is 2, your answer is n plus 1. Okay, so this thing we can write is, what you are doing is, whenever you want to take a XOR from 0, okay, you want to take a XOR from 0 to n, that can be written as, if n modulo 4 is equal to 0, if it was equal to 0, you return n. For 1, you return 1. For 2, you return n plus 1. For 3, you return 0. So when for all the multiples of 4, your answer would be 0. For all multiples of 4 plus 1, your answer would be n. Okay, plus 1, your answer is 1. Okay, so for 0, your answer was n. So for multiples of 4, your answer was n only. For n plus 1, your answer would be, this was 1. So the answer would be 1 here. If n modulo 4 is 2, then for 2, your answer was n plus 1. So you would write n plus 1 here. And for the remaining case of n modulo 4 equal to 3, your answer is, for 3, your answer is 0. Okay, so like if you don't know, like this is how you, in order of 1 only, you can compute the XOR from XOR of all numbers from 0 to n. Okay, so just on the basis of its remainder with 4, if it is 0, you answer n. If it is 1, you answer 1. If it is 2, you answer n plus 1. If it is 3, you answer 3. So this way, you can just find out the XOR of all the numbers up till n in order of 1. Okay, so they would follow this pattern only. This pattern is going to get repeated. n, 1, n plus 1, 3. Then again, n, 1, n plus 1, 3. n, 1, n plus 1, 3. This is getting repeated, you can see. Okay, n was 0, then 1, then n plus 1, 0. n, 1, n plus 1, 0. This is n, 1, n plus 1, 0. Okay. This pattern is going to get repeated. So this was the first part. Okay, that XOR of all the numbers from 0 to n. That is that you can compute. Okay, now the main part, how do you compute this thing? XOR of all non-beautiful numbers from 0 to n. Okay, let's see. So let's see the definition for beautiful. What was that? Is x modulo 2 to the power I should not be equal to k. Let's analyze this condition. I am telling that the condition for beautiful is x modulo 2 to the power I should not be equal to k. So what would be the condition for not beautiful is, it should be equal to k. Okay. We are analyzing for not beautiful. We have converted the question into finding all the XOR of numbers which are non-beautiful. So for a number to be non-beautiful, its modulo with 2 to the power I should be equal to k. Now, what is taking modulo with 2 to the power I? Okay, you have some number x. Okay, let's say I'm writing this number in binary. Let's say this is some number. Okay, in binary. If this is your ith bit, let's say, then taking modulo with 2 to the power I, what does that mean? That means if this is your I, your 2 to the power I means 2 to the power I means this number. Okay, let's say you have x equal to 10. So 10 would be 1010. If you take modulo with 2 to the power 3, what is 2 to the power 3 is this number. So 10 modulo 2 to the power 3 is 8, you get 2. What you get? Okay, this was your number 10. You take modulo with 2 to the power 3, take modulo with this 100. The number you get is 2, which is 0010. Basically, whenever you take a modulo with 2 to the power I, you are making all the bits here 0. That's what you are doing. You are just considering, okay, what is happening with taking modulo with 2 to the power 3 is you are removing all the multiples of 2 to the power 3 from that number. Okay. The remainder on dividing it with 2 to the power 3 is going to be all the bits that are set this side. Okay, this was 2 to the power 3 here. So all the bits that were set this side, if you unset them, because they all would be multiples of 2 to the power 3. Okay, these bits would be multiples of 2 to the power, including this bit also. Okay, including this ith bit. They all would be multiples of 2 to the power 3. So those multiples can be removed if you're taking modulo, and only these numbers would be left. Like any number x, what is that? That is x written in binary is x expressed as sum of powers of 2. Okay, so all the powers greater than I, okay, all these bits, all the powers greater than I, their modulo with 2 to the power I would give me 0. So only the numbers only the bits less than I, they would be remaining in the number when you take with modulo 2 to the power 3. Okay. So basically what is happening is whenever I'm telling that x modulo 2 to the power I should be equal to k, it means if in the x I'm ignoring all the bits above I, if these bits are ignored, then these bits, all the bits less than I, okay, only consider these bits. If this number is equal to k, that means it satisfies this condition. That's what it means. Okay, so first if we take the first I bits, or like I bits or I minus 1 bits, if the first bit is the 0th bit, so till I minus 1 it has I bits. Okay, so if you are taking the first I bits of x, if that is equal to k, then you say that it is not beautiful. Okay, that's the condition for not beautiful. Now, what you need to do is you need to take the XOR of all the numbers that are non-beautiful up till n. Okay, f of n is that XOR of all the numbers from 0 to n, XOR of all the numbers from 0 to n that are non-beautiful. Okay, let's say you have I equal to 3. It means you are looking at the first 3 bits of the number, and you have n equal to let's say some 40. Okay, so from 0 to 40, okay, so from 1 2 3 4 up till 40, how many numbers would be there whose, if you take the first 3 bits, that would be equivalent to some k. Let's say k is 3. Okay, so how many numbers are there whose, if you take the only the first 3 bits, that's equivalent to 3? What is 3? 3 is 1 1. This is 3. Okay, this is what my k is. So if you look at the numbers, if you look at 1, that is 0 0 0 1, 2 is this, 3 is this, 4 is okay. Let me just write down all the numbers. Okay, let's say I have these numbers. Now I want to find out how many numbers whose, if you consider only the last 3 bits, because when you are taking modulo 2 to the power 3, it means all the bits before that becomes 0. So these last 3 bits is what we are considering. If that is equal to this 3, then you are taking that number. That number is not beautiful. You have to take the XOR with that number. So this you are not taking. This you are not taking. This number you are taking. Okay. So this number you are taking. This number again you are not taking. This you are not taking. This you are not taking. These you are not taking. Okay, after that, let me write 11. Okay, this number again, last 3 bits are not equal to 3. Last 3 bits are not equal to 3. Here, if you see the next number, the last 3 bits are equal to this 0 1 1. Okay, so this number again you would take. Okay, this number again you would not take. So what all would be the numbers that you are taking is this number, which is 3. Okay, 3 itself would be taken. Then you have this number, which is 11, where you have 0 1 1, and this bit is also set. Okay, the next number that you would take, what that would be, okay, that would be some number. Okay, the last 3 bits would be 0 1 1 for sure. After 1 you have 0 1. Okay, this would be the next number that would be taken. Like, can you understand that? Okay, because I am keeping constant that the last 3 bits is 3. Okay, last 3 bits is same as my k. Now for the remaining bits, all the numbers, okay, if you have all the combinations of the bits, those would be the numbers, those would be the different numbers that are coming. So basically the numbers that we are taking is 0 1 1, remaining bits 0. Okay, this is 1, then 0 1 1, this bit is set to 1, remaining is 0. Then 0 1 1, this is 1 0. Okay, then you can have 1 1, then 0 1 1, then 1 0 0, then 0 1 1. Okay, so this 0 1 1 is fixed, and if you look at this number, it would be 0 1 2 3 4. So all the numbers, like, basically if you remove these bits, then all the numbers from 0 1, like if these bits are removed, this number is equivalent to 0, this number is equivalent to 1, this number is equivalent to 2, this number is equivalent to 3, this number is equivalent to 4. They are being taken up till where? Up till the numbers is less than n, less than equal to n. Till there we have to take. Okay, so if you take the XOR of this, all these numbers, what it would be? For this part, it is, you can again see 0 1 2 3 4, XOR of all consecutive numbers. So basically this part would be the XOR of all numbers from, okay, now basically the XOR of all numbers from 0 up till some number, the last ending number. If you right shift it, basically remove the last 3 bits, then whatever number you get here, XOR of all numbers from 0 till that number would be this part. And what would be this part? Okay, when you do a XOR of 2 of them, it would become 0. then one of them it would become 0, 1, 1. Then again a XOR, overall it would become 0. So if the count of these numbers is even, it would be 0. If the count of these numbers is odd, this would be 0, 1, 1. Okay, so this part just depends whether the count, sorry, this part just depends whether the count is odd slash even. For even, it would be 0. For odd, it would be k. You can say, okay, 0, 1, 1. So k or 0, whether the count is odd or even. Now, how would you find the count, or till where you have to take? How would you find this last number till where you have to take the XOR? Okay, that the condition was that that last number should be less than n, less than or equal to n. Okay, so first of all, in n we would see, okay, let's say in this case we had n equal to 40. Okay, here I had taken n is equal to 40. So what would be 40 if you write in binary? That would be 32 plus 8. 32, 68, and then 4, 2. Okay, this is what 40 is. So if you look at 40, so just before 40, what's the last number that is coming in this pattern? Okay, so 40 is this number, 101 triple 0. So just before that, what's the number? So just before 101 triple 0, I would have 011. Okay, and 111. This is n minus 1. Okay, so in 011, we have all the okay, so before that we would have some 011 and this k. Okay, so this would be the last number basically for n equal to 40. This 100 and 011, this would be greater than n. You can see 101 and okay, sorry. Before 101 we had, okay, I'm sorry. Before 101 we would have 100 and 111. This would be n minus 1. Okay, this number. Okay, so basically 100 and 011 would be before n. Okay, this one would be less than n. If you had the next in the order was 101, 011, this number is greater than n. Okay, I hope you can understand. This number would be greater than n because n is this. Okay, so this part when kept same, 000 is there, so this number is greater than that, so this is greater than n. And when this part is only reduced, so all the numbers would be less than n. Okay, so for this we found out that this is the number just less than n. Now in general, how would we find? We would look at our n. From that we would remove the first I digits. Okay, and then this would be the number. Okay, so either we would have, either my last number would be, after removing these digits we got 101. So either we would have 101 and then a k. Okay, so k was 011. Either it would be this, or just before that it would be 100. So this number minus 1 is 100 and a k here. Okay, so 011. So whether it would be this number or this number depends on whether this number is greater than n or less than n. Or we can say that this thing is greater than this thing or less than this thing. Okay, so basically this is k, and how do we get this number is when we take n modulo 2 to the power I. Okay, so I'm telling if n modulo 2 to the power I, basically the last I digits of n, if that number is greater than k, okay, so if that number is like greater than equal to k, we take this number, else we take that number. Okay, if that is less than k, then we take a number just before that. So basically what are these numbers? How do we create these numbers? Is if this is greater than equal to k, then we are creating this number. What is this number? This thing is k, and this thing is what is obtained from n. Okay, so if you right shift n by I digits, okay, so our n was 101,000. If you remove these three digits, you get this. That is what removing these three digits means, right shifting by I. So n right shift I, with that you get this part of the number. Okay, so in n right shift, with n right shift I, you get the left part of the number. Okay, and whatever is the left part of the number, basically, okay, that's the left part. So either it would be this if this case is satisfied, else it would be right shift I minus 1. Okay, that is the left part of my number. Okay, which would come here. Okay, let's say I'm telling this as x. So my final XOR of all non-beautiful numbers from 0 to n, that would be, so this part is XOR of all numbers from 0 till x. Okay, first I calculated my x, what would come here. Okay, for the last number, this part, this x is either n right shift I or n right shift I minus 1, depending on this condition. Okay, so I got my x, which is n right shift I or n right shift I minus 1. Now, once I got my x, I would take the XOR of all numbers from 0 to x in order of 1. I can compute that using the above thing that I told you. This way, you can calculate XOR of all numbers from 0 to n. So I calculated XOR of all numbers from 0 to x. This way I got this part, and this part is just if x is even. Okay, so if like if this number, okay, 101, if that was odd, this was an odd number, then 1 2 3 4 5 6 times we are having it. Okay, so if this is this count is just this x plus 1, because 0 1 2 up till x we are going. So a total of x plus 1 numbers are there. Okay, so a total of x plus 1 values are there. We are taking a XOR of this thing x plus 1 times. So if x is if this count is odd, means x is even. Count is even means x is odd. Okay, so that would just depends on whether this count is odd or even, or I can say x is odd or even, and it would interchange because depending on x plus 1. So x here, 0 here, k here. So if my x is even, like, sorry, I had opposite. If my x is odd, that means x plus 1 is even. So even times if I'm having, my XOR would be 0. If my x is even, it means I'm having x plus 1 as odd. So odd times XOR would result in k. Okay, so I've computed this part is 0 or k. This is computed here. This part is computed like this. So my final this whole value would be this part left shifted by I XOR with this part. Okay, that why I would get my complete this number XOR of all the non-beautiful numbers up till n. Once I got the XOR of all non-beautiful numbers up till n, I'll XOR that with my XOR of all numbers up till n. Okay, so once I've got XOR of all non-beautiful numbers up till n, XOR with XOR of all numbers up till n will give you my function of n. And my final answer would be f of r XOR with f of l minus 1. I hope it is clear to you. We'll look at the code so it becomes more clear. Okay, so I've created a all XOR function to calculate XOR of all numbers from 0 to n. So if same thing I've written, if modulo is 0, I return n, 1, n plus 1 or 0. Okay, so this thing that I told you, this function, if it is 0, then n, so n 1, n plus 1, 3. Okay, so n 1, n plus 1, it was 0 here, sorry. I've written 3, but it was 0. Okay. So this all XOR function is written first to calculate the XOR of all numbers from 0 to n in order of 1. Okay. Now this is my f function f. Okay. My function which is calculating f of n. Okay. So f of 1 n that I wrote you there, which is XOR of all beautiful numbers from 0 to n. Okay. Now how I am calculating f of 1, f of n is I am calculating XOR of all numbers from 0 to n, XOR with all non-beautiful numbers from 0 to n. So first in my answer, I will store XOR of all numbers from 0 to n. Okay, XOR of all numbers from 0 to n, all XOR function I've called, stored that in my answer. Okay, now with my answer, I am now in another variable, I'm calculating this thing. Okay, how I'm calculating this thing? So first I would calculate x, which is n right shift I. Okay, so first I would calculate this part. Okay, this part of the last number. Okay, these are all the non-beautiful numbers that I'm having up till n. What is the last number up till n? That is n right shift I. As I explained you, what would be my x? X would be n right shift I if this is greater than equal to or -1 if this is less than k. So I initialized my x as n right shift I, and if n modulo 2 to the power I was less than k. Okay, so if n modulo 2 to the power I was less than k, it means I'm going to the else part. I do a minus minus from my answer. Okay, I do x minus minus. Okay, so if this condition is satisfied, that means I would have n right shift I -1, and if it is not satisfied, I would have n right shift I in my x. So this way I've computed my x. Okay, so if x is computed, so here what I would have, here I would have XOR of all numbers from 1 to x. Okay, this part is XOR of all numbers from 0 to x. So that I have computed all XOR x. Okay, all XOR x gives me the left part of my answer. Okay, now this right shift I, okay, this way I would get this number. Okay, with 0, this as the 0th bit. Now I have to right shift it by I bits. Okay, this right shift I would give my remaining number, the left part of my final answer, this right shift I. To that I want to add this part. Okay, now this part would be either 0 or k depending on whether x is odd or even. So if x is even, I would XOR it with k. Otherwise, XOR with 0 would remain the same. Okay, so if x is even, I would have a k. So I would XOR it with k if x is even. This way I got my, in my remaining variable, I got this part, which is the XOR of all non-beautiful numbers. Okay, XOR of all non-beautiful numbers from 0 to n, that I am got in my variable rem. That rem XOR with my answer would give me f of n. So in answer, I XOR my rem, because initially XOR of all numbers, XOR with XOR of all non-beautiful numbers. This way my answer is computed, I return my answer. Okay, this is how my f of n is getting computed for a fixed I and k. Now, what would be in my actual function? What I would write, I take the input L, R, I, and K. L, R, I, and K is taken an input. So if I is 0, that in this case I'm just handling separately, then I just see out 0. Okay. XOR of all beautiful numbers from 0 to 0. Like 0 is not a beautiful number. So I would answer 0 only. You have nothing in the range. So for I equal to 0, I would answer 0. Otherwise, my answer would be f of r XOR with f of L minus 1. Okay, so f of r for given I and k XOR with f of L minus 1 would be my final answer. As I explained, the final answer would be f of r XOR with f of L minus 1. Okay, so I hope this thing is clear to you. What would be its time complexity is, this is my input part. This is just a basic if condition. Now this function XOR with this function. So what's the complexity of this function? Here I am computing an all XOR. This function is running in order of 1. Okay, this ALSOR function is just for if conditions, so it is order of 1. Then this right shift is order of 1, this is order of 1, this ALSOR again order of 1, then a right shift I. Okay, so like this right shift I may take an order of I. Okay, this is, you can say, order of I. Okay, right shift are there, and then this XOR, this XOR, this XOR, everything is done. So this is basically done in order of I. Okay, you can say. So my finally this function is running in order of i's or with order of I. So my overall time complexity, you can say, is order of I only for each test case. Okay. So for t test case, it would be t into I, which is well accepted for I is only up till 30. So order of I is well accepted. So I hope this problem is clear to you. Okay. The main thing was just thinking in bitwise how the XOR is working, how modulo 2 to the power I. Okay, a lot of learnings from this. This all XOR function is a question in itself, how you compute the XOR of all numbers from 0 to n. Okay, it's a standard question in itself. And then how you are just using that thing was the main thing here. Like if you have to compute the XOR of all non-beautiful numbers, understanding that taking modulo 2 to the power I is basically just considering the first I bits, and then all those numbers having first I bits equal to k, they would be this number with all 0, or 1 with this, 2 with this, 3 with this, 4 with this, that way. Okay, so when you remove the first I bits, they are actually 1, 2, 3 up till some number x. How do you find that number x? Is the first number which is less than equal to n. So n right shift I gives you that x. Okay, if that particular would be taken, if that is greater than equal to k, then okay, these things are managed. I hope this problem is clear to you. Okay, so I think we can move to the next problem now. So the next problem is problem G, which is an interactive problem. Okay, so I'll tell you what this problem is saying, that basically you are given an n. Okay, it means you have n books from 1 to n. Okay, so you have n books, they are numbered from 1 to n. Okay, among those n books, 3 of the books get missing. So someone, there's a thief which takes 3 of the books. Okay, so those 3 books are A, B, and C. Those are all 3 distinct books. Now every book has a exactly 2 copies. Okay, in the library, so or whatever in the library, there are 2 copies of every book from 1 to n. Among them, 3 distinct books are taken away. So one copy of them is taken away by some thief. Now you just need to find out what all those 3 books are which are taken away by the thief. To find that, what you can do is you can do a XOR from the range of L to R. You can, in every query, you can query a XOR from L to R. What that would do is that would give you the XOR of all the books from L to R. Okay, what is the final XOR of all the books numbered from L to R that are present? Okay, so if there are 2 books with a number L, their XOR would become 0. And if there is only 1 book, their XOR would become L, the value of that book. Okay, so for those for those distinct variables, if that is coming in the range, that XOR would be given. Okay, like we'll discuss that. So you can see for the first query, okay, in you had like this, n was given as 6. So there are 3 of the books are missing. Those missing books are actually for the first test case. You can see the missing books are 2, 3, and 5. So you can see this 2 is occurring 1 time, 3 is 1 time, 5 is 1 time. But all the remaining books, 4 is here, 4 is here as well, 2 times. 1 is 2 times. 6 is occurring 2 times. So this 1, 4, 6, they are occurring 2 times. but 2, 3, 5, they are occurring only one time. Okay, so there would be exactly three of the numbers from 1 to n. Okay, three of the numbers that would occur one time, and the rest all the numbers would occur two times. Okay, so now in this you can do the queries. Okay, so first you can see you did a query of 1 to 1. It means XOR of all the books numbered from 1 to 1. So there is a book numbered 1, book numbered 1. So 1 XOR 1 would result in 0. You get 0 as the output, as your as an input for your query after your query. So when you query 2 XOR 2, XOR 2 comma 2, it means XOR of all the books numbered from 2 to 2. So there is only one book numbered 2. So XOR of just 2 with no number, it would result in 2. Okay, 3, 3. So now 3 is occurring, again 3 is occurring only one time. So XOR of 3 would give you 3. And then you have 4, 6. So from 4 to 6. So 4 is occurring 2 times, 4, 4. 5 is occurring one time. 6 is occurring 2 times, 6, 6. So this XOR would be taken. So 4 and 6, they would cancel out and 5 would remain. So your final output would be 5. So basically from the query, you can understand that what you are doing is whenever you do a query from L to R. Okay, so basically let's go there. So you have n books. Okay, this n is going up till, you can look at the constants, n is up till 10 to the power 18. So you have many books and you can do at max 150 queries only. Okay, only 150 queries can be done at max, and you need to find that the three ABC, you need to find the three books that are missing. Okay, that are occurring one time, that you need to find. So you have a n, let's say I'm denoting in a number line. This is book number 1. This is book number n. Okay, that way we have. So among these n books, there are three of the books. Let's say book number A, book number B, and book number C. Three of the books that are only one time present. Rest all books are present two times. Rest all of the books are present two times, but these three books, A, B, C, they are present only one time. And in query, you can do a query of XOR LR that would give you a XOR of all the books from the range L to R. So let's say L is here, R is here. It would give you a XOR of this full range. Now, when you do a XOR of this full range, all the books that are occurring two times, their XOR would be 0 always. Okay. So because they are occurring two times, so XOR of X XOR X is 0, you know. So for whenever you take a XOR from L to R, XOR of all the book, if there is some A or B or C present in that range, then only you would get something. Otherwise, you would get 0 as the answer for your query. That's the first observation. Okay. One more thing, if you want to check whether a book is among my answer, it is single time or two times, then you can do a XOR, you can write a query of XX. That way, if that query returns a 0, it means X is two times. And if it is greater than 0, it means X is one time. Okay, so basically X is one of your answer. You can confirm. So you can always check whether X is your answer through this query. But if you one by one check for all the numbers, you have 10 to the power n up till 10 to the power 18. You can't do 10 to the power 18 queries. You have to do it within 150 queries only. So what you would do is you can do a query for a range. If you do a query from 1 up till n for the whole range, what is the output you would get? You would get the XOR of ABC. All the remaining XORs would be 0. Okay. When you do a query from a range in which you get only A, okay, then your answer for your query would give you A. Basically, you will get your answer if you have only A in there. And if in the query you have two of the values B and C, let's say, then it would give B or C. Okay, and if all the three values are coming in the query, you would get A's or B's or C. Okay, so the first thing is what you can do is like in these interactive problems, you have to do something like a binary search kind of thing. Okay, because you have 10 to the power 18 and you can do only 150 queries. So log of 10 to the power 18 would be something like 60. Okay, so if you can implement something in log n or 2 times, 3 times log n, that would be fine in 150 queries. So what I would do is I'll do a binary search kind of approach. I'll initialize my low here, high here. Okay. So first I would do the XOR of this whole range from 1 to n. This XOR of this whole range from 1 to n. This is going, what is this going to return me? This is going to return me A's or B's or C definitely. Because all the three numbers A, B, and C are going to come in the range from 1 to n. So by doing this query, I know the XOR of all the three numbers ABC. Let's say I denote it by XOR 3. Okay, XOR of all the three numbers. Okay, by doing this query, I get my output in XOR 3. I know the XOR of all the three numbers. Now I would take a mid. Okay, let's say I take this as a mid. Okay, then I would do the XOR from low till mid. Okay, when I do this XOR from low up till mid, okay, there can be like few cases. Either in this range, okay, when I have some numbers, this is 1, this is n. In between somewhere you have like, if you have this range initially, your, okay, this is 1, this is n. Initially your low would be set here, high would be set here. Now in between there are some numbers A, B, C are present here. So if you take mid as here and then you take this zone, there can be three cases. Either all the three A, B, C, they lie on this side. So your this XOR would return, okay, this would return 0. Or it may be the case that these three numbers A, B, C, all of them lie in this range. Then this XOR would return you the XOR 3 that you got initially. Okay. Or it may be the case that they get divided. Okay. Or it may be the case that you have a 0 here and here. And when you do a mid, maybe A is here, B and C are here. Okay. Either this case or A and B would be here, then you will have the mid, then you would have C. Okay, one of these cases would happen. So first of all, when you have this case, okay, so when you take like in every time, what you would do when you have this, when you do a XOR from 0 to mid and you get 0 as output, it means your answer lies to the right of mid. So what you would do, you would update your low. Okay, for when you get 0 as your answer, you would update your low as mid plus 1. Okay, it means you make your low here, your answer lies somewhere here. Or if you get XOR 3 as your answer, that means your answer lies in this range. Okay, your all the three numbers lies in this range. You can reject, this range can be rejected. So if you get this as your answer, you would do high is equal to mid. Okay, so if you take your high here, your answer lies in this range, for sure. Okay, so for these two cases, you are just reducing your ranges in order to reach this A, B, C. Okay, so when you have from low to mid, you get XOR of 0, you increase your range. Okay, this whole range gets rejected. Your low goes here at mid plus 1. You consider this as your new range, in that you again apply the same thing. And if this is equal to XOR 3, the XOR of all the three numbers, it means you reject, this whole range gets rejected, and you do high is equal to mid. So high would move here, and this is your new range in which you would again search. Okay, that way you would move. Then there a case can come then that you have that you have a low here, you have a high here, and the mid is dividing it into two parts. That means when you take this query, okay, so when you do this query from low to mid, you get something which is not equal to 0 nor equal to XOR3. Okay, so if you have only A or only B and C, XOR of two numbers or one number, that means that's neither equal to 0 nor equal to XOR of all the three numbers. Then in that case, you know that you are basically, your mid is between, okay, your mid is, some of the numbers is lying to the left of mid, some of the numbers is lying to the right of mid. Now, if you take now you need to find out whether you have this case, one number is to the left, two are to the right, or this case where one number is to the left and like two numbers are to the left and one number is to the right. So how do you find this case? Okay, now when you whatever is the answer to this query, okay, let's say the answer to this query is X. What would be the XOR of the remaining from mid plus 1 to high? Okay, do you need to do an extra query for that? No, you don't need to do an extra query. This would be whatever the XOR of all the three numbers is. From that, if you XOR X, you get the XOR of this side, the remaining numbers. Okay, so you know the XOR of left side from low to mid is X. XOR of right side from mid plus 1 to high is XOR3, XOR X. Okay, you know both the values. So you know for sure either this X is equal to A if there is only one number, or this X to the right one is equal to C if there is only one number. So you can check whether the left range has only one number or the right range has only one number. Okay, so if in the left range there is only one number, just check whether this X is one of the numbers. If so, how would you check? You do a XOR of, you do a query XOR XX. By doing this query, you can check whether X is there or not. Okay, X is one of your answer among ABC or not. If X is one of your answer, then okay, you got one of your answer. Now search for your remaining answer from this range. Or if this was not your answer, it means the remaining XOR3, XOR X that you got, that is one of your answer. Search in this range. Okay, so that way you found one of your answer. Okay, so once you did this partition, you got one of your answer. Either this, if you check if X is a valid answer, then it means X is one of your answer. In the right range, check for this number, like take this as the XOR of the two numbers that you are searching for, and again check. Or if X is not your answer, that means in the right range, whatever you got, I'm telling this as X2, it means X2 is one of your answer. Okay, then check in the left range with X as the XOR of the two numbers that you have. Okay, so this way I got one answer by doing this binary search. One answer I got, and I got a XOR2. You can represent XOR2 as the XOR of remaining numbers, remaining two numbers. Okay, and a range where this XOR, these two numbers is lying. In that, again, you can do a binary search. Now, okay, you have a low high. In that, you know there are two numbers, some B and C are there, which are my remaining two numbers. Okay, and in XOR2, I know the XOR of these two numbers. Again, I would check. Okay, so if my mid is somewhere here, then for this would be 0. Okay, so if my XOR from 0 to mid is 0, then I'll do the same thing, low as mid plus 1. And if my XOR from, if my mid was somewhere here, that means my XOR from low to mid was equal to XOR2. In that case, I would reject the right range, would get rejected, and I would do high is equal to mid. Okay, so like for two variables, again, I would apply the same logic, same binary search, that if I get a 0, low equal to mid plus 1. If I get a equal to XOR2, high equal to mid. So that's why I'm rejecting the range. And then a point would come when I have a low, high, mid, and this is dividing the two numbers. Okay, when this is dividing the two numbers, my XOR from low to mid would neither be 0 nor be XOR2. Okay, it would be something else. And whatever that is, if that XOR is X, then X is one of my answer, and the remaining, which is XOR2, XOR X, that is one of my other answer. Okay, so that way I got my final answer as, okay, then I would just append these into my final answer, the X and XOR2, XOR X. I got my B and C, and I would break out. Okay, I got my B and C, I would break out. Okay. So this was a solution, but there is one small problem with this solution is what I'm telling. Initially, when I was doing a searching with three numbers, okay, I had these three numbers, okay, from the range 0 to n. These three numbers lies somewhere in my range. Okay, then I took a mid and I did XOR from 0 to mid, and I checked whether this XOR, okay, so if all the numbers lies to the right of mid, it was this case, all the numbers, this is my mid, all the numbers lies to the right of mid, then I get XOR from low to mid as 0. So I move my low as mid plus 1. When the XOR of all the numbers is to the left of mid, then I get the XOR as equal to XOR 3. XOR 3 I initially only obtained as the XOR from 1 to n, the XOR of all the three numbers. Then I do high as mid. But what if XOR 3 is equal to 0? What if XOR 3 is equal to 0? Then what we would do? Okay, the three numbers that we have, let's say A, B, C is A is 1, B is 2, C is 3. Okay, the XOR of 1, XOR 2, XOR 3 is equal to 0 actually. Okay, so if we get the XOR of those three numbers as 0, then when we get the query for low to mid as 0, we don't know whether that 0 is because all the numbers in this, there is no ABC in this range, or it's XOR 3, all the three ABC are in the range. Okay, this 0 and this XOR 3 are the same, so we don't know we need to go to the right or we need to go to the left. So then this case has to be handled separately, that when the XOR of the three numbers is equal to 0, then we cannot apply this binary search. Okay, whenever I want to reach towards the ABC, okay, there would be two cases. This is 0, this is n. This ABC is somewhere in this side. So with mid, I did a XOR and I got 0. Now I don't know, I want to move to this side to get to this ABC, or maybe this ABC is somewhere in this side. So I would have to move to the left range to get to this ABC, because this XOR is 0 for when this ABC is not there. And when this ABC is there, then still the XOR of A's or B's or C is also 0. So that case has to be handled separately. But if the XOR of the three numbers, XOR 3, if my XOR 3, the XOR of three numbers is not equal to 0, then I can, that previous logic was completely fine. That way I can move towards this ABC. Then after some time, I would cut it from between. Then I would have two cases, two numbers to the left or one number or two numbers to the right. For that case, I can just check if I have one, the XOR that I get, if that is equal to, if that is one of my answer, then I'll take that and search for two numbers in the right. Then for two numbers, again, I would run a different binary search and search for two numbers in same way. Now for two numbers, I would never have, like XOR2 would never be equal to 0. That I can say is for sure, because these are two distinct numbers. You know, the XOR of two distinct numbers is never 0. XOR of three distinct numbers can be 0, but XOR of two distinct numbers is never 0. For XOR of two numbers to be 0, both the numbers should be same. And we know that the three ABC are distinct is given in the question. So XOR of two distinct number is never 0. So this binary search would never fail. But this binary search can fail where the initial binary search where my XOR 3 when it becomes 0. So how can we solve that problem? So for that, what separately I would do is if XOR 3 is equal to 0. Okay, that case. So that case I'm handling is, okay, I know the XOR of the three numbers is 0. So how would those numbers be? If you look at the numbers, let's say A is 1, B is 2, C is 3. This is one case where XOR of ABC is 0. What is 1? 1 is this, 2 is this, 3 is this in binary. So their XOR is 0. It means, okay, these are 0, 0, ignore them. The most significant bit is here. Okay, so for all the, after this, for all the bits, two of the numbers bits would be set. Okay, so number of set bits in the three numbers would be 2 or 0. Then only their XOR would become 0. Okay, the final XOR is 0, 0, 0, 0. Okay, so if you look at this position, two of the bits are set, and in this position also two of the bits are set. Okay, so for the most significant bit that is set in any of the numbers, there I know for sure for two of the numbers the most significant would be set. For one of the numbers it would be some different. So I know for sure that if you take the most significant set bit for the three numbers, if their XOR is 0, then there would be two numbers having the same most significant bit and one number having a different most significant set bit. So I know MSB of two of the numbers would be same. Okay, so you know for MSB of this is 2, MSB of this is 2, like for I equal to 1, whatever you say, and for this it is 1. And MSB of other number would be lower. Okay, so what we can do is one by one check, like if I'm checking for all the numbers having MSB as this. Okay, so all the numbers having MSB as I. What all numbers have MSB as I? 2 to the power I, 2 to the power I minus 1 minus 1. All these numbers have MSB equal to I. Okay, so if you take the XOR of all these numbers, like the XOR of if you take a query from 2 to the power I to 2 to the power I minus 1 minus 1, that query would return, sorry, I plus 1. Okay, if you do a query from 2 to the power I to this, that query would return how many of numbers from your answer whose MSB is I. Okay, XOR of them. Now you know that when you move from smaller to greater MSB, okay, for one of the numbers your MSB would be small and two of the numbers would have the same MSB. So the first time where you get the answer for this query as, okay, so you do a query of this type. Okay, basically all the numbers having MSB as I, if you take their XOR, then if you're doing like one by one, the single number that you get, okay, which has a lower MSB, that would come first. Okay, so if you get the answer for this query as 0, it means none of the numbers with MSB I is present in my answer. If you get the answer for this query as greater than 0, it means there is at least one number with MSB I which is present in my answer. Then the first time that you get such, there would be only one number. Like in this case, if you see, if you do the query for I equal to 0, okay, you do 2 to the power 0 to 2 to the power 1 minus 1, which is 1 to 1 only. Okay. So numbers having MSB as 0 is only 1. Okay, if you take the query from 1 to 1, okay, this query is going to give you 1 because you have A equal to 1 here. So there only you can say that you got your answer 1. If you are taking like for this, after that, if you are going to I plus 1, then what would happen that like the first I for which you get some positive as your query, that would be that MSB, which is a different number, which is the smaller among the three numbers. Okay, what I'm telling is among the three numbers, the smaller number would have a different MSB and the two bigger numbers would have the same MSB. That's what I want to tell, that when the XOR of the three numbers is 0, it means the two bigger numbers have the same MSB and the one smaller number has a different MSB. So if you do a query for all the numbers of the same MSB, then the smallest query for which you get some answer, that would be the smaller number. Okay, so for I equal to 1, here you get 1 as your answer. So then you get this, you found this 1. Okay, so that way you can find the one of the numbers. Once you have found one of the numbers, then for the remaining two numbers, you know from XOR 3 was 0 only. So whatever, if A is that one number, the XOR of the remaining two numbers is also A. So your XOR 2 is equal to A. With this as XOR 2, you can apply the this second binary search can be applied here. Only the instead of the first binary search where you were searching for one number among the three numbers, that is replaced by this searching for the starting from I equal to 0 for XOR of all the numbers with MSB I. That's what you are searching there. Okay, like one more example I'll show you. What if A is, let's say, 4, B is 5 and C is 6. I think their XOR would also be 4, 5, 6. 4 is 1, 0, 0. 5 is, okay, let's say 5, 6, 7. 5, 6, 7. Okay. Instead of 5, let's take 1. Okay, let's take these numbers. Okay, let's take this example in order to understand. 2 is 0, 0, 1, 0. 4 is 0, 1, 0, 0. 6 is 0, 1, 1, 0. Yeah, their XOR is 0. Okay, so let's say you have these as A, B, C. Then what is happening is, what I'm telling is, for the two greater number, they would have the same MSB. They both have MSB as, okay, if I'm writing in 0 based, 0, 1, 2. They both have MSB of 2, MSB of 4 and 6, both are 2. Okay, this is the MSB. Now, but for A equal to 2, MSB is 1. Okay, so if you start with I, checking with I equal to 0, all the numbers with MSB 0, their XOR. Now, none of A, B, C have MSB 0. Okay, A has MSB 1, B have MSB 2. So when you do a query from 2 to the power I to 2 to the power I plus 1 minus 1, for I equal to 0, okay, you get, and the answer for the query you get is 0, because all the numbers whose MSB is 0, they are not present in ABC. When you take I equal to 1 and do a query from 2 to the power I to 2 to the power I plus 1 minus 1, then for all the numbers with MSB 1, okay, so I equal to 1, it means this is 2 to the power 1 is 2, 2 to the power 2 is 4 minus 1, 3. So 2 and 3, they are the numbers with MSB 1. Among them, among 2 and 3, their XOR 2 is one of the present numbers. So you would get the answer for this query as 2. You would get 2 as the answer for this query, because for all the numbers among 2 and 3, this 3 is present 2 times, but 2 is present 1 time. 2 is one of my answer. There only we would stop and say that yes, 2 is one of my answer, and the XOR of my remaining 2 numbers is also 2. Okay, so XOR of 4 and 6 was 2. That you get that the XOR of all the 3 numbers, if it is 0, then one of the numbers is 2, XOR of remaining 2 numbers would be 2. So with taking XOR 2 as 2 and searching for the range from 2 to the power with I equal to 1 you got, so search from the range from 2 to the power 2. Okay, take this as low, from this as low and high as n, this as XOR 2, do the second binary search to find B and C. Okay, I hope you understood. So let's look at the code. Okay, so what I'm doing is take n as input. First query would be XOR from 1 to n. This is going to give me XOR 3. Okay, so initially I would compute the XOR of the 3 numbers. So a query from 1 to n would give me XOR 3, XOR of the 3 numbers. Now I'll set my low as 1, high as n, and this XOR 2 would be computed. Vector int answer, in this I would push back all the 3 numbers one by one when I confirm that this is my answer. Now if XOR 3 is 3, if XOR 3 is 0, if the 0 case, for the 0 case, I run a loop for all the MSBs from 0 till 60. I would check for all the numbers having MSB I. So XOR of 2 to the power I to 2 to the power I plus 1 minus 1. Okay, this is my query. Okay, 2 to the power I to 2 to the power I plus 1 minus 1. Now, if the output that I get, it is X. If X is greater than 0, then X is one of my answer. In answer, I would put back S, X, and my XOR 2 would also be X. The XOR of the remaining 2 numbers is also X. My low is set to 2 to the power I plus 1. So I would search for those 2 numbers as their MSB would be greater than I. So I would start searching from 2 to the power I plus 1, and I would break out. Okay, so this way I am computing for XOR 3 equal to 0 case. Else, I would run my binary search while low is less than equal to high. So else I'll run my binary search with 3 numbers. My mid is low plus high minus low by 2. I would run a query for XOR from low to mid. Okay, from low to mid I run a query. In X I got the answer for the query. So if X is 0, it means in the left side I have no numbers. So low is set to mid plus 1. Search in the right side. If X is equal to XOR 3, it means all the 3 numbers are in the left side. So high is set to mid, search in the left side. Else, if none of these 2 are satisfying, it means the mid is dividing it into either 1 number in the left and 2 in the right, or 2 in the left and 1 in the right. So I would check whether we have 1 number in the left. So if 1 number is in the left, it means X is that possible number. First, I would check that X should be less than equal to mid, because that's lying to the left and it's the XOR. So if X is less than equal to mid, and I check XOR of X, this way I would check if the output that I get, which is Y, is equal to X, it means X is one of my answer. I'll push back X in my answer vector, and I'll say the XOR of remaining 2 numbers is XOR 3, XOR X. Okay, now XOR 3 was the XOR of all 3 numbers. XOR with X will give me the XOR of remaining 2 numbers. And for the remaining 2 numbers, I'll search to the right side. So low is set to mid plus 1, and I'll break out. Okay, now my job is done for this binary search. Then I'll do for the 2 remaining numbers, I'll do a separate binary search. Okay, else if these conditions are not done, that means the right side, that means in the left side I have 2 numbers, and the right side I have 1 number. So the right side number was XOR 3, XOR X was the number to the right. That is my answer. That is my possible, that's my one of my answer, because on the left side I have 2 numbers. That's why their XOR is not one of my answer. So whatever I have to the right side is my answer. In the right side, I have XOR3, XORx is the XOR of right side. And my XOR2 is X. Okay, so X was the XOR of left side. That's what we have, two numbers in the left side. So that is the XOR2. And my high is set to mid. So this is pushed back my answer. Now I would search for the two numbers in the left side. So high is set to mid and break. Now, after this is done, I have to do a binary search for the remaining two numbers. So again, a low less than equal to high, mid is low plus high minus low by 2. Then I do a query from low till mid. Okay. And then whatever I did a query from low till mid. I get my output of that query in X. If X is 0, mid would be set to mid plus, low would be set to mid plus a search in the right side. If X is equal to XOR2, search in the left side, high is set to mid. Otherwise, mid is dividing one number in the left and one number in the right. That means X is one of that possible number and XOR2, XORx is the other number. So I got X and XOR2, XORx as my answers. I'll break out of the while loop. Okay, then I'll just print my answer for all the numbers in my answer array. See how I ended. Okay, I printed my answer. I hope this is clear to you. At max, how many queries we would have? So this binary search would run at max log of 118 times. So this binary search would run at max 60 times. In this binary search would run again log of 118. This would run at max 60 times. So in total 120 times, either we would have 120 times this and this one extra query. Okay, so 121 times. And for final checking, we would have maybe one query, 122, which is less than 150, the query limit that we were given. Okay, and in this case also, at max 60 MSBs we are checking. So at max 60 queries here. Okay, this would also run at max. So either we would run 60 times this, or in the else part, we would run 60 times this. Okay, so in both the cases, we are running 60 times only, plus this 60 times. Okay, so we are running at max 120 queries only. Okay, so I hope this problem is clear to you. So thank you very much for joining in. Goodbye.